Good morning to everyone. I'd like to welcome attendees in person and online, particularly members of the Alaska Board of Forestry and the Citizens Advisory Committee of the Tanana Valley State Forest. This workshop, Managing Public Forest Lands for Carbon Sequestration in Alaska, is sponsored by the Alaska State Society of American Foresters and local chapters. SAF members include foresters, scientists, land managers, and associated natural resource disciplines. Forestry can be broadly defined as managing forest vegetation and ecosystem services for present and future needs of society. Key purposes of professional societies like SAF are public and professional education and awareness, in addition to outreach on technical and policy topics. I'm Tom Paraguay, a retired wildlife biologist who came to Fairbanks 40 years ago, almost to the day, to attend this university. My co-chair for this workshop is Mr. Chris Maish. Chris is retired from the State of Alaska Division of Forestry and Fire Protection, where he was a division director of State Forester, and he's a past president of Society of American Foresters at the national level. Dr. Scott Ruff was a collaborator in conceiving this workshop. He's a professor here at the International Arctic Research Center with a background in forest ecology and nearly 3 decades of experience in modeling climate change to understand implications for natural resource management. He helped us consider topics and identify speakers you'll hear today. We thank Dr. Ruff and UAF for providing this meeting forum today as part of the university's public outreach mission. Unfortunately, he had a work conflict and is not in Fairbanks today. We also thank Andrea Watts of the Northwest office of SAF for help with advertising. The main reason for this workshop was hearing recurring questions at public meetings over the last couple of years about carbon sequestration and potential effects of projects on existing forest uses. This is a new topic to many Alaskans and includes broader considerations compared with timber sales that are administered on state lands by the Alaska Division of Forestry and Fire Protection. We expect this brief overview of carbon forestry today will answer some questions, pose others, lead to further discussion, and inform public comments on proposed projects. This topic for Alaska forests was first considered in the late 1990s, and this is a proceedings of a reforestation needs and opportunities for carbon sequestration in Alaska. This was a year 2000 workshop sponsored by the Alaska Reforestation Council, and it was published through the Agriculture and Forestry Experiment Station here at UAF. Early proposals for carbon sequestration on public lands in the interior, I recall the first one being in 2003, were for different carbon markets and before an insurance risk pool existed for unanticipated losses such as wildland fire. It has become more common since the 1990s. Carbon sequestration contracts of various types in different markets presently exist on private forest lands of Alaska Native corporations in Southeast, South Central, and Interior Alaska, which represent a range of forest types and environments. The earliest reference I found was for a project on private lands was on Afognak Island from 2006. Presently, there is a feasibility assessment being developed on the first proposal for contracts on public lands owned by the state of Alaska, specifically here in the Tanana Valley. This is occurring under regulations passed from legislation in 2023 and is being administered by the Alaska Department of Natural Resources, Office of Project Management and Permitting. Be aware there is a separate carbon leasing program by DNR, often called carbon capture and storage. In contrast to carbon forest projects that are above ground in biological time, in other words, subject to releases back to the atmosphere, carbon capture and storage occurs in bedrock pore space, such as oil or gas basins. CCS is a relatively permanent sequestration in geological time. The Alaska Center for Energy and Power and Institute of Northern Engineering here at UAF, in coordination with DNR, have been holding town hall meetings around Alaska and are a source of information on CCS. So this forestry workshop today through Zoom is being recorded, and the transcript will be housed after a short delay on the SAF website, along with Zoom chat questions to speaker panels, some of which may not be able to be addressed due to time constraints. For guests online, please keep your audio muted and conserve internet bandwidth by keeping your camera off unless called on to ask a question. Please raise your hand in Zoom to ask a question during panels, or you may enter your questions in the chat box. To raise your hand in Zoom, click on the react symbol on the bottom of the screen, and you will see the option to raise hand. We will try to answer questions in the order asked, switching between in-person, audio online, or in the chat. So this is an informational workshop sponsored by a professional society, not a meeting for public testimony. We hope that information provided today and questions from the audience or from invited speakers will help inform members of the public who wish to provide comments to DNR on the carbon forestry proposals for state lands that you'll hear about today. So I'll be chairing this morning's session that's focused on the scientific background for carbon offset projects. And Chris Bache will chair the afternoon session, which addresses management topics, including economics and legal considerations of carbon registries. We'll have brief breaks mid-morning and mid-afternoon. And at the end of each session, we'll have speakers serve as a panel for questions and discussion. And Chris and I will moderate those panel sessions. For people here in UAF, please mute your cell phones. The lunch is on your own from 12 to 1. There are cafe options on upper and lower campus, or you can eat your sack lunch in the IARC lobbies on the lower levels. The afternoon session will resume promptly at 1 p.m. The emergency exit is out these main doors where you enter. There are elevators immediately across the hall. If you go to the left around the corner, that's where the restrooms are and the water fountain. Caution that the water fountain is currently pushing out about 18 to 20 inches, so push the button before you stick your face down there. And if you go just beyond that, those are the stairs as part of the emergency exits. And finally, for SAF members who wish to earn continuing forestry education credits, we have a sign-in sheet that I'll pass around here now. You can put your name and email and your SAF or certified forester ID on there. For people online, members online, we'll have instructions on how to submit your name and SAF or certified forester ID near the end of this workshop. So I think those are the main things to cover. We've got just a couple of minutes yet before we get started. Are there any questions?
Do you have a count of the numbers online?
There's 28 right now online.
I think there were
29.
I think there were 74 or 5 that signed up to be online at some point today, and roughly 17, 18, 19 here in person. In the meantime, I will unpin myself here. Judy, do you want to try sharing your screen?
Uh-oh, sure, yeah, let's try this. Can you see that?
Yep, you can see it. Excellent, all right. So our first speaker is Eugenie Yuskirchen. Her talk is going to be, she's got the title on it right there, we'll go with that. So Eugenie is an associate professor of ecosystem ecology and global change modeling at the Institute of Arctic Biology and the Department of Biology and Wildlife here at the University of Alaska Fairbanks. Research in her lab at UAF focuses on climate feedbacks from Arctic and boreal ecosystems using field-based and modeling approaches. She received a PhD from Michigan Technological University in Forest Sciences, where her dissertation focused on optimal timber harvesting strategies for carbon sequestrations in the forests of the Great Lakes region. And although her office is in an adjacent building here on campus, she's presently presenting virtually from Finland, where she is on sabbatical and it is early evening.
All right, thank you. Yeah, so thank you for having me. And I guess the fact that I'm here in Finland and zooming back to you underscores how interesting and important I think this issue is. And I'm really glad that you organized the workshop. So I'm going to kind of start off with the bigger picture in terms of carbon cycling and look at first the present day global carbon cycle, and then talk about a remaining carbon budget, and that is how many carbon emissions we can emit to keep global temperatures under a certain threshold. And then I want to talk more about the forest carbon cycle and permafrost ecosystems in particular within forested ecosystems of the boreal forest, and also talk about carbon sequestration in general. So going back to this global carbon cycle, each year the Global Carbon Project, which is a large multi-institutional institutional estimate of the global carbon budget each year, and also the nitrous oxide budget and the methane budget is put out. And so recently in December of 2024, they put out the global carbon budget from 2023. So it's always a little bit lagged behind. And so the next few slides I present to you are based on some of this information from the Global Carbon Project, and this is their homepage. So if you want to learn more about what they're doing and some of their estimates, they have a really great amount of information that's very accessible and easy to understand. So I would recommend checking their webpage out if you're interested. So as you have probably all seen this graph from the atmospheric CO2 measurements at Mauna Loa. This shows the increases of atmospheric CO2 beginning in the late 1950s all the way up to just a few days ago, essentially. And so we can see that right now we're a little bit above 420 ppm carbon dioxide in the atmosphere. And this is actually the highest level that we've seen in definitely the last 800,000 years, but possibly even going back more than 2 million years ago. So it's an unprecedented amount of atmospheric CO2 in the that we have, and it's also increasing at a rate that's actually faster than anything that we know in terms of the rate of increase in the atmosphere over at least the last 66 million years. So it's unprecedented in a number of ways. And so there are lots of other greenhouse gases, but today I'll be focusing primarily on carbon dioxide. It's the most powerful per molecule of warming compared to other greenhouse gases, and also just simply the sheer amount of carbon dioxide that we've managed to emit into the atmosphere from our activities. And the fact that it sticks around in the atmosphere for hundreds to thousands of years makes it really our biggest challenge in combating climate change. It's also important to note that we hear a lot about methane, particularly in Alaska, emissions from lakes and wetlands. And methane is actually quite important. I'll say a little bit about it later on, but after a certain amount of time in the atmosphere, methane actually oxidizes and becomes carbon dioxide as well. So the carbon budget, what is it? It's all the emissions and removals of carbon dioxide into the atmosphere and out of the atmosphere that are a direct result of what we're doing. The biggest part of this is the emissions from combusting fossil fuels, so coal, oil, and gas. That accounts for about 90% of all CO2 emissions. And then we also have to think about cement production, which also is a small component, but significant because it involves limestone, which contains a lot of carbon. And so the remaining emissions into the atmosphere, they come from land use change, and that's primarily from deforestation. And so fortunately, of all the CO2 emitted into the atmosphere, there's only about half of it that remains. And that's the part that leads to climate change because of the direct relation between atmospheric CO2 and temperature. But then the other half that is not in the atmosphere is removed, and it's removed by the vegetation and photosynthesis and also diffusion from the oceans. And so because of this removal, the impact is only really about half of what it would be if we didn't have these natural CO2 sinks. When we talk about the global carbon budget, the units are kind of crazy. We're talking about like 1 billion tons of carbon dioxide. And so 1 billion tons is a gigaton, or 1 times 10 to the 15th grams, which is a petagram. And then a kilogram of carbon is equivalent to 3.664 kilograms of carbon dioxide. And then 1 gigaton of carbon is then 3.664 billion tons of carbon dioxide. And so this schematic from the Global Carbon Project quantifies the sources versus the sinks. So we have the atmospheric sources, and we know that through data from energy statistics and cement production. And then the land use change is down below, about 10% is from deforestation. So those are our main sources. And then our sinks, the atmosphere, that's from the concentration data I was showing you earlier, it's atmospheric concentration. And then the other 2 sinks are the land sink and the ocean sink. And so we know the land use, the land sink and the ocean sink, because we can apply process-based models that are constrained by observations. And so if you add up all these sinks and all the estimated sinks and all the estimated sources, we come up with this budget imbalance, which is about 4%, or about minus 1.6 gigatons of carbon dioxide per year. And so I'll say a little bit more about that in a minute, but just keep that in mind, that we're not able to perfectly balance our carbon budget based on the data and models that we have. If you look at this spatially, the fossil fuel emissions, you can see those are concentrated here in the first panel. They're concentrated up in the northern hemisphere, versus these land use emissions. They're concentrated more in the southern hemisphere. And these are, again, like I said, due to deforestation, primarily in South America and parts of Africa. And then the ocean sink, the blue parts of the graph representing the sink are seen mostly in the North Atlantic and also in the Southern Ocean, whereas the sources from the ocean are primarily within the tropical ocean. And the land sink is dominated by the tropical forests that we haven't managed to cut down yet, as well as the temperate forests and also the boreal forests as well. If we look at the land use change a little more closely, thinking about deforestation, you can see that the annual emissions from deforestation between 2014 to 2023, they actually are declining, but they're still high. They're still about 3.7 gigatons of CO2 per year. And then you can see in the green below that the carbon dioxide removals from forest regrowth or afforestation are about 1.9 gigatons of carbon per year over the same period. It's interesting to note here that if you look at the deforestation for shifting cultivation versus the forest regrowth and shifting cultivation, they're actually very, very similar numbers, a little over 2 gigatons of CO2. And so back to this idea of this budget imbalance in the global carbon budget. So the black line here is the mean uncertainty across all the different sectors. And so that was that, the black line is, for example, in 2023, it was at 0.4 gigatons of carbon per year. But the red is important to think about as well, and that is the total uncertainty across all the sectors. So if you think that 0.4 gigaton was actually pretty good, it's not really that great if you think about this red band over here, where we have all the uncertainty across the different sectors. And when we think about this uncertainty, there are a lot of things that we actually aren't even taking into account, and I'll say more about that in just a minute here. But this gets into the idea of the remaining carbon budget. And so if we want to figure out how many more emissions we're allowed to emit into the atmosphere to constrain temperatures below a certain threshold, for example, the Paris Agreement that we just withdrew from again, has about 1.5 degrees Celsius target of mean increases in future temperature. And there's some papers out there that show that any more than that can lead to some pretty catastrophic changes. So 1.5 degrees C is what we're aiming for. And if we're aiming for that, then we think, although there is that uncertainty I was just showing you, that we're allowed to still emit about 130 to 500 gigatons of carbon dioxide over the next 3 to 7 years. And that's the maximum that we're allowed to emit. And then if you compare that to what we've already emitted from about the pre-industrial age to present, that's about 2,500 gigatons of CO2. So we're not really able to emit that much more carbon dioxide to constrain future temperature. And it's been shown that in order to constrain these temperatures, we have to actually not only reduce our emissions, but also start to rely on carbon dioxide removal techniques, or CDR. And so right now, with the statistics I was showing you earlier in terms of our ability to regrow trees and regrow areas that were both deforested and turned into cropland, we're actually in some ways doing pretty well there. That's become about equivalent to 5% of annual fossil CO2 emissions, and about 1.9 gigatons of CO2 per year, like I said earlier. But then if you think about these other techniques that we're just starting to look into, like direct removal of carbon dioxide through carbon dioxide capture technologies, and then something else called enhanced weathering, which is performed in agricultural fields to apply minerals like basalt that react with CO2 to form very stable compounds in the carbon compounds in the soil and then permanently sequester CO2. If you combine these two types of technologies, although we've been hearing a lot about them, they haven't really started to take much effect yet. It's only equivalent to about 1/1,000,000th of our annual fossil fuel CO2 emissions. So really right now, it's the trees. Trees are where it's at here in terms of carbon dioxide removal techniques. But looking across the various biomes on the planet here, this graph from the Forest Service I always like to show that illustrates really nicely the difference between the above ground versus the below ground biomass across biomes. And so it's very obvious here that the tropics, if you're thinking about trees, that's where it's at if you want to store biomass in the above ground component. They also store a fair bit of carbon in the soils as well. But then if you go over to where we are in the boreal moist and the boreal dry forest, you can see here that it's really in the soils. There's a little tiny tree there atop the boreal moist, but there's really nothing on the boreal dry. So if we want to think about carbon sequestration in the boreal region, we really need to think about the soils and maybe a little less about the above ground biomass. And so what is that below ground biomass, or the below ground component? It's a lot of it is peatlands, and a lot of the peatlands are permafrost, particularly in Alaska. The permafrost carbon pool is about 1,600 gigatons of carbon, 1,600 to more recent estimate is about 1,700. And so you compare that with all the carbon in the soils and the vegetation of 2,300 gigatons of carbon, you can see that permafrost is really important in terms of carbon storage. So, like I said, 16 to 1,700 billion tons of organic matter are stored. This has been built up over thousands of years. And so the amount of carbon stored in the permafrost, we think it's about 4 times more than the total amount of CO2 that we've emitted in modern times. So if we start to see permafrost thaw, it could potentially be emitting a large amount of carbon into the atmosphere. In Alaska, of course, you've probably all seen this graph, permafrost distribution. Here we are in the boreal zone in the discontinuous area permafrost in Alaska. A lot of the type of permafrost we have in interior Alaska and also up north, it's the Yedema type of permafrost. And this is really significant because it has about a 2 to 5% carbon content. And that's about 30 times greater than what we have usually in mineral soils. And so this is this Yedema permafrost. It's formed from alluvial deposition. It's called the syngetic type of permafrost. We also have other types of permafrost as well, peat accumulation and also climate variations as well. But the Yedema is really important if we're thinking about carbon sequestration. And so then one question that a lot of scientists have become interested in recent years, what is the magnitude and timing of permafrost carbon release into the atmosphere in a warmer world? And so we've been able to actually model the spatial distribution of permafrost for a while. So this was something I did back when I was a postdoc at UIF, actually doing some modeling. And so I was able to model here what was then I considered the present day distribution of permafrost in panel A there. And then I took that panel A and I overlaid it on panel B, so 2040 to 2050 permafrost. And you can see there in panel C that there are a few little pink dots that start to poke out. And those are the areas from which the permafrost has thawed by 2040 to 2050. And then if you go up to 2090 to 2100 and you overlay that on what I consider the present day distribution of permafrost, you can see that there are a lot of pink dots poking out. Conforms to about 600,000 square kilometers of permafrost lost, estimated by 2090 to 2100. And so we've been able to do that for, well, since I did it back in 2006. And that's great. But then the question there is, what are the CO2 and CH4 emissions from this thawing permafrost? And this is a question that we're still a little bit hung up on. And so when I was talking before about that uncertainty in our global carbon budget, it doesn't even take into account permafrost. It's maybe starting to a little bit, but not really. And we have estimates. We have a really wide range of estimates of thawing permafrost in terms of release of atmospheric CO2 between 22 to 432 gigatons of CO2 released. And that's under, if we were to model this with a strict climate mitigation scenario, we really only have 1.5 degrees C warming. But if we have more warming than that, then it's possible that we could release up to 550 gigatons of CO2. But these are all underestimates, actually, because these models generally don't take into account things like abrupt thaw. If all the permafrost in various regions were to all of a sudden reach some point and thaw abruptly. And we're also not very good at thinking about the wildfire impacts on permafrost thaw when we're doing modeling. So these are underestimates, and they're not taken into account this. Remember what I said. I said we had about 130 to 500 gigatons of CO2 that we were allowed to release in order to limit our emissions of warming to 1.5 degrees Celsius. But if you think about permafrost, that could all be taken up by permafrost thaw. So it's really significant. So what's the mechanism for this release of CO2 from the soils into the atmosphere? Just going back quickly, back to the basics here, to the forest carbon cycle, where you have plant uptake, photosynthesis, or all the plant uptake in a given period of time is gross primary productivity. The plants are they're respiring, and that's autotrophic respiration, releasing CO2 back into the atmosphere. There's then the below ground processes, which includes the below ground plant biomass, as well as the soil carbon the soil carbon pool, where the permafrost is, and then you have litter, and then you have within this soil carbon pool, you have this heterotrophic or soil respiration, which also releases CO2 into the atmosphere. And then going out the bottom here, you have dissolved organic carbon and inorganic carbon moving into aquatic ecosystems, which are, again, generally sources of CO2. And then I think it's important to think about, if we're thinking about carbon sequestration, the term net ecosystem carbon balance. And so we have net ecosystem carbon balance is equivalent to net primary productivity, where again, net primary productivity is gross primary productivity. So all the photosynthesis minus autotrophic respiration. So net primary productivity minus heterotrophic respiration, so the soil microorganisms respiring, minus all fire emissions, minus any timber harvest, and then also including biogenic methane emissions. So you take all this into account and you get your net ecosystem carbon balance for a given ecosystem or landscape. And you can imagine measuring this and estimating it is tricky. But if we go back here to the permafrost and the mechanism for release of CO2 from the permafrost, we have the historic conditions versus today's conditions in the graph here on the left. And what you can see here is that historically we had an active layer that was at a certain depth, whereas under this warming, we have a thicker active layer. And with this thicker active layer, we have more permafrost that the microbes can, or previously frozen area that the microbes can munch on easily. And so during the growing season, the microbes are doing that. They're breaking down the plant matter and whatever they like to munch on, and they're releasing carbon dioxide and methane. But the plants are counterbalancing a lot of this. So in boreal and Arctic tundra ecosystems, we actually see that during the summer, the ecosystems are a net sink of carbon dioxide because the plants are compensating for what the microbes are emitting. But in the winter, when the plants are dormant, there are a number of different microbes that are still active in the soil, and so they can continue their activity. And this is where we're beginning to see emissions. It's during the larger emissions. It's during the fall shoulder seasons, and sometimes much later into the winter as well. In order to understand the emissions from permafrost, we have a pan-Arctic network of eddy covariance measurements. Eddy covariance is a direct way to measure both CO2 and methane coming from and going into ecosystems. And so this is our network around the Arctic. You can see that some of these are annual sites. It's difficult to take measurements annually because the power requirements are pretty high. So keeping things going year round can be challenging. So a lot of the sites are simply growing season sites. But we use this information to look at and upscale across various biomes and ecosystem types. And this is a nice paper that just came out last year that shows ecosystem flex upscaling across permafrost and non-permafrost ecosystems in the north. You can see that the boreal forests are actually here estimated to be a net sink of CO2, the yellow triangle there. But if you take into account the boreal fires, on the other hand, in the boreal forest, they're a net source. Boreal wetlands are a large source of methane, but a small sink of CO2. And then we also hear a lot about lakes and methane emissions, which is shown here. So that's one estimate. You can see these measurements end in 2020. And one thing that we're trying to get better at doing is thinking about updating these types of figures more contemporaneously. So going, say, from all the way up to 2024. Other recent synthesis papers that came out looking at across this eddy covariance measurement scheme is this one that was published in Nature Climate Change also last year. And this is really, there's this difference between permafrost and non-permafrost ecosystems in terms of the trend, in terms of annual net carbon ecosystem exchange. And that's And that's interesting. And then another really recent synthesis that just came out was also in Nature Climate Change. And it's saying that the Arctic boreal zone is becoming more of a source. And in general, we know that tundra is becoming more of a source in particular, but and the boreal zone, which we've always thought of as a large carbon sink, is becoming much less so when we start to think about fire emissions. And so if you think about fire emissions, this increasing trend in the Arctic boreal zone is no longer significantly, statistically significant. So those are just three really recent syntheses in terms of thinking about carbon uptake across the Panarctic, and I think are quite relevant in terms of both their permafrost messages and their fire messages for Alaska in terms of carbon sequestration. And so finally, just to summarize what I just said, if we want to meet the aims of keeping temperatures below 1.5 degrees Celsius as outlined in the Paris Agreement, we need some sort of carbon dioxide removal technology. And right now, afforestation has been our main source of that. And if we think about the boreal region in particular, possible sea emissions from thawing permafrost are not included in current emission scenarios. But most of the carbon in the boreal region is stored in the soils, the permafrost and the peatlands. But also then, since these are long considered a sink of carbon, this combination of wildfire and permafrost is potentially shifting boreal regions to a source of carbon. And this then creates a lot of challenges if we're thinking about carbon sequestration strategies in boreal regions, in particular in Alaska. All right, thank you. Sorry about the technology. Any questions, or maybe you should just email me or something.
Thank you, Eugenia. We appreciate you sticking with us through these challenges. We'll need to go ahead and move on to kind of keep on schedule. We really appreciate you presenting here, and have a good evening. We're not going to ask you to stick around here midnight for the panel, but thank you very much for your presentation.
Yeah, thanks for having me.
Our next speaker is Uma Bhatt. Uma is a professor at the UAF Department of Atmospheric with research appointment at the UAF Geophysical Institute and the International Arctic Research Institute. She has an undergraduate degrees in mechanical engineering and Russian from the University of Pittsburgh, and earned a master's and a PhD in atmospheric and oceanic sciences from the University of Wisconsin-Madison. Her current research interests include climate drivers of tundra vegetation change, seasonal forecast skill of sea ice and fire weather in the Arctic, and co-production of research that has relevance for stakeholders.
Great, thank you. Thanks, everybody. I was glad to be given this task of summarizing what is the state of the climate of Alaska, and I really relied heavily on a lot of publications that have come out of UAF, and particularly for the historical, and then some other publications for the future. So the way I divided this up, I'm going to talk about the historical and future temperature, precipitation, and wildfire. Those are kind of the things I was going to focus on, relevant for carbon sequestration. And my take-home messages are: it's gotten wetter in Alaska, and at least the future projections suggest it'll continue getting wetter. The snow season has gotten shorter over the historical period, but as we look into the future, it actually looks like there might be more snow falling during wintertime in boreal Alaska. And as we precip versus temperature, I think it again becomes, it's going to be challenging how we project what fire is doing, right? Both of those factors, but getting warmer does make it more likely to have more dangerous fire weather. Rick Toman does a great job of making plots and updating current trends. If you don't look at his Substack blog, it's great. And he makes excellent figures. And this is a recent figure from Rick, which shows the 10 warmest years in red, the 10 coldest years in blue, and then the annual temperature. So things have changed in Alaska over the last 60 years. We'll talk more about that. So as I prepared this talk, I thought about what questions did I want to answer? How has temperature varied in the recent past over Alaska? Similarly, how has precipitation varied and how has wildfire varied? And how will temperature, precipitation, wildfire vary going into the future? This was a paper we put together as part of the team led by Tom Ballinger for the National Climate Assessment. We prepared these figures for that, so I actually, for the historical past, I've used mostly material from that paper. Do you all know what this plot is showing? You see, do you know what these lines are? Climate divisions, yes. So a lot of what I will focus on will look at the climate divisions in 2, 3, 4, and 5, which are the boreal forest. So most of my focus, when I pull out time series, will look at those regions, since that's of most interest to you. All right, so annual temperatures have increased. This is a plot from Ballinger et al. That shows the annual change in temperature. And for a lot of our work, we summarize it over climate divisions. That gets rid of some of the issues we might have with data limitations by averaging over an area. And you can see overall from 1957 to 2021, it's warmed. It's warmed the most over the North Slope because of the impacts of a changing, retreating sea ice, which helps the land warm up a lot more. You also see large warming. The second largest warming is in the southern part of Alaska, but that depends on the data set. If we look at another data set, those trends in Southeast are much smaller. And the changes in the boreal part of Alaska is roughly 0.4 to 0.3, and this is degrees Celsius per decade. I guess ask me questions if you have any questions about the plots. I didn't make tons of pictures, but it's picture heavy, so please interrupt me. Again, are you most interested for forest health in winter or summer? Summer temperatures are what came to mind to me, but I'm not sure. The temperature, these are the temperature trends from the annual broken up into the seasons. The greatest increases are in the cooler seasons, December the most, and then March, April, May, springtime, and then fall. Again, very closely tied to the cryosphere, the presence of sea ice or the presence of snow. And summer, we also have warming, but those magnitudes are smaller. But overall, these are mean temperatures. I think when we think about carbon sequestration, we're probably interested in extremes or variability of temperature. And this shows the lowest 1% temperature. So these are the coolest 1% of the temperature distribution, and it's shown as a grid. So the plot on the left shows the mean of those values. So see the coldest temperature up north, it gets warmer as we go south. And then the plot on the right shows the trend of those temperatures per decade. And the hashing shows their significance. So over a lot of largest increases in the north, quite a significant and large increase of those coolest temperatures. So as this annual temperature has gone up, those coolest temperatures have gone up more than the warmest temperatures. And this is the warmest temperatures, means 29 and 21 Celsius. Warmest means are in interior Alaska or the boreal forest. And then the right-hand side shows the trends. Most of the trends are along the coast that are significant, but the warmest temperatures are not warming that much. The biggest difference to get that annual warming is coming from the coolest temperatures. These are the top 1%. Does that make sense? Now, I always like to look at time series because I think they tell us a lot about what's going on, not just the spatial trend. And this is a combined time series of those west of the interior boreal forest, including the west coast. So I just combined all of that data. So this is the temperature anomaly. I took the mean out. It's June, July, August. over this period of 85 years from 1940 to 2024, its temperatures have gone up. 3 month temperatures in the summer have gone up to 2.5 degrees Fahrenheit. And we can see we have a lot of variability from year to year, and the warmest summer up there is our summer of 2004 when we had the really big fires. You know, we spend a lot of time looking at these time series and asking, you know, is the variability changing? I know my student is convinced that over the last, I guess, like decade, that temperature variability's gone down. So, possibly. So let's next move on to precipitation. Now, temperature is, we have a lot more confidence in temperature. We struggle with precipitation data. And for a lot of our spatial analysis right now, we're using something called ERA 5. And this is a gridded product that is, it comes from a weather forecast model, but it's informed by observations. And it does a good job in Alaska when you compare it to station data. Even station data has problems. There's a lot of discontinuities. And some of those are removed in the ERA 5. So again, it's not perfect, but it is the best that we have, and we put a lot of a reasonable amount of confidence in this new reanalysis product. So if we look at the blue means an increase in precipitation, and so all of Alaska on the annual timescale, precipitation is increasing, and this is percent change. So while the North Slope looks huge, it's a percent change, and overall there's much less precipitation there. So this is so it can be scaled onto one plot. Again, the largest percent increases are in the North Slope, followed by Southeast. And if we use a different data set, the NCEI data set, which is from NOAA, the trends are actually wetter over most of the state, and they're actually wetter in interior Alaska. So there's a bit of uncertainty in this. But getting wetter over since 1957, so over the last 65 years, 64 years. If we look at the seasonal breakdown of the changes in precipitation, in the wintertime, DJF, the precipitation's increasing. In spring, it's varied, it's decreasing in the southern part of the state. And then in the summer, again, it's more increasing than decreasing, but there's some negative trends, it's mixed. Again, that could be partially due to variability. If we look at fall, we see that Southeast is yellow and that there it's drying. So a bit more varied in spring, summer, and fall, but increasing. Now, what's happening to kind of the extreme precipitation? And one of the ways we measure this is 5-day precipitation amounts. And the mean values are shown in the left-hand side, typically 4 to 8 centimeters over most of the state, much higher over the coastal regions. For the mean 5-day precipitation, and then the trends show increases, strong increases on the North Slope, increases in interior Alaska also that are significant, and then kind of mixed increases in south and decreases in southeast. So overall, when we're getting 5 days of precipitation, those maximum values are increasing. So those storms that are coming or storms that are developing are more vigorous, which is what you'd expect in a warmer climate as the hydrological cycle gets stronger. We look at the precipitation anomalies. Again, a lot of this one needs to look at more regionally, because in different regions, you can see different types of variability. If you look at the coastal part of Western Alaska, you see this multi-decadal variability. And I think that could be very useful in doing some sort of predictions for, what decade might be good for the forests, or when we might want to sequester carbon. I don't know exactly how this is going to be done, but I think looking at all of this data regionally can give you more insight on what are the long-term drivers. And they're different in different parts of Alaska. So I hadn't, so now snow off. Snow is a really important part of the story, particularly for fire and for forests. The plot on the left shows the snow off trend. And I actually made this plot a while ago, and I don't remember if this was per decade. I think it's per decade, but that's huge. It's like 7 or 8 days earlier per decade from over the last 42 years. So it's like 40 days. I don't think it's the total. I think it's per decade, but I'm not. I apologize. I looked at it this morning. I didn't remember. But this has been very striking all over Alaska that the last day of snow has been getting earlier. And when we think about fire weather, that's when the fire season begins, and that's when things start drying out. And that becomes a really important measure of how we might have a fire season. So typically on average, snow off has gotten 15 days earlier in 2023 than in 1960. And the biggest changes have been in southeastern Alaska. It's really retreated more. We've looked at that in more detail in other work. Another measure that we use to look at dryness of fuels is something called the SPEI index. And I pulled out a picture from Josh Walston's paper at the top, and this shows an SPEI 12, which is the year-long SPEI. We went back to 1925, and it shows 3-month dry periods are shaded. So the 2005 fire shows up in northeastern Alaska. This is the Tanana East, the YK Delta, Yukon, not YK Delta, Yukon Flats, predictive service area. So you did not all of them show up. So SPEI, his paper was all about which of these drought indices work in Alaska. And in the end, it was kind of a mixed bag of a story. But I pulled that one out because we looked at SPEI for in an attribution paper for the fires of 2019. And what we found is this is June, July, August SPEI, different colors for the Kenai Peninsula when we had the fires in 2019. And that's the last year show there that all 3 months the SPEI was negative. When it's negative, that means things are very dry and very hot. And it's a measure of drought that's commonly used in other latitudes. And it seems to do a reasonable job here, not perfect. And I guess one thing that struck me about this plot was that it seems that we're having more summers with increased negative values of SPEI in the Kenai Peninsula. And we haven't done this for all of Alaska yet. So again, drought indices could be a good measure of fuel, the availability of fuels to burn. Now, if we look at fires, I think probably this crowd, I don't need to show this plot, you probably know this plot very well, but this is showing in red the years above 1 million acres, which are the ones that require more resources. And since 2000, Alaska's had 9 summers where more than 1 million acres have burnt. And in the previous 20 years, Alaska had 5. So this rate of bigger fires that require more resources has been increasing. So that's why we want to understand what might be driving so we can prepare better and keep people safe and do a good job. So this is this plot on the left is from the Alaska's Changing Environment, a recent document that IARC prepared. There's some great graphics that summarize what's going on in Alaska. And this is a graphic put together by Brian Brettschneider of the snow season from 1998 to 2024. The left-hand side is October, the right-hand side is May, June, and it's showing, for all of Alaska, it's showing that this snow season is decreasing. The decrease is greater on the end of snow season side than on when snow appears, but that's also decreasing. So again, the snow season's getting shorter. But it may be, more snow may be falling. Now the plot on the right takes a bit more explanation. This is from a recent paper by Peter Bieniek. one of the questions in our fire predictability group was to understand how important is snow for fire weather? And I had always been taught it doesn't matter because the moisture in the snow is very limited, that it doesn't really last for very long. So if you have a lot of snow in the spring, or if it's not likely to have a climate impact on the soil. But we think something else is happening. And this plot shows, the plot on the right shows different parts of Alaska, the different southwest, north slope, south central, western interior, eastern interior, and the plots I've been showing you combine those, the interior regions. It shows that it's showing in each region took the total acres burnt over all the years and compared it to the different terciles of when snow off occurred, whether it was late, whether it was middle, or whether it was early. So the bigger that red bar is, that means on the north slope, an early snowmelt was associated with almost 90% of the acres burnt. And so this plot in south central and eastern and western interior show a significant, there's a significant relationship with how many acres were burnt and when the snow went off. So less snow than 60% area burnt in eastern interior. So something is leading to the persistence of temperature and precipitation once the snow goes away. And I'll tell you at this point, we don't understand what that process is. We're working with it. So I think so we look for these sort of signals that tell us early in the season how might the season evolve. And this is a plot that shows lots of stuff. And the bottom line is that Alaskan fires coincide with warmer, drier summers, but not always. And that's the piece we're really trying to understand what's going on. So on the x-axis is the temperature anomaly, and this is for all of the boreal forest region. On the y-axis is acres burnt in all of Alaska. And then the size of the dot is associated with acres burnt. So the smaller dots are at the bottom, and as you move up, the dots get bigger. This associated with millions of acres, and that big brown dot on the right-hand side is 2004, and then the colors show what the precipitation was like. So in general, the really wet years tend to be 1 million acres or less. So if you know your summer's going to be wet, it's not likely to lead to a big fire year. Anyway, I think the goal for us is to understand what are the other factors in a large scale climate that push us to one side or the other. Now let's look at the future of temperature and precipitation. And this is work from a recent paper by Mizukami et al. In Climate Services. And they took, if you look at temperature change by the end of the 21st century and precipitation change, models that tend to get warmer tend to have more precipitation. So they took 40 different CMIP6 models, climate models, and came up with this analysis. And then they picked the red ones and they downscaled those to high resolution, 4 kilometers over Alaska and Hawaii. And our group that's funded by CASC is currently downscaling the historical and the future. So hopefully within 8 months or so, we'll have a lot of new data available to do kind of more detailed analysis for Alaska that I think could be relevant for the carbon sequestration. We look at, these are the patterns of warming in their, each line is a season. The top is the historical mean, so that's the climate model present day. And then as we move down, we see warming occurring. By the time you get to 2040 to 2070, the greatest warming is along the coasts where the ocean's warming, the sea ice is going away. Less warming during the summer months throughout. And even when you get to 2070 to 2099 at the bottom row, the summer interior is the least likely to warm based on this on average of many different climate models. So again, greatest warming in the north, less towards the south. We look at precipitation. The top line is the historical precipitation and I guess this is annuals. So overall, it's all positive. You don't see red dots there. And the largest increases are in the southern part of the state. And also the other, on the right-hand side, it's showing evapotranspiration, which is also positive. So as the climate warms, you're evaporating more also. So both of those are competing effects to what that might do to fire. Then this is a plot that shows what happens to snow water equivalent over the snow water equivalent over the near future, and the late future shows increases in interior Alaska and decreases along the coastal regions as you have warmer oceans and warmer air coming from the south. And the plot on the right just shows the decline of glaciers, that those white glaciers are shown in the historical period, and then they become white and red. Red means decrease, but white means they're gone. So again, my take-home message is it's gotten warmer, it'll get warmer, but we have large interannual variability. And that's one of the things our climate analysis strives to understand that to help us predict what might happen in the coming summer. It's gotten wetter and precipitation is projected to increase over Alaska. I think 20 years ago we weren't as sure of that. I feel like over the last 20 years we've converged on that thought. The snow season's gotten shorter, and we expect it to get shorter in the future, but more snow is projected to fall during the cold months. And I think fire danger is expected to increase with warming temperatures, but it's unclear how that might be modified by precipitation. And in all of this, I haven't even discussed lightning, because if we have a lot of precipitation in the summer, it could be convective, and that could be associated with lightning. Lots of competing efforts. But I think going forward, I want to thank my fire weather predictability and downscaling team and other collaborators. And this work, most of this work was funded by the Alaska EPSCoR Fire Project and Alaska CASC. And the downscaling products that we're creating, I think, will be able to answer a lot of more detailed questions than we can with these other work from other groups. Thank you for your attention.
In the interest of time, we'll probably hold questions till the panel on that. Thank you very much. Share. That Nathan Lajewski has worked for over 15 years at Chugach Butte in Anchorage and is presently the forestry director. He's a certified forester with the Society of American Foresters and is currently chair of Alaska State SAF. Nathan serves on the board of forestry and has extensive experience working on multiple California cap and trade forest offset projects within the state of Alaska. He obtained his bachelor's and master's degrees in forestry from Northern Arizona University.
Well, hi, I don't know if you guys can all hear me there in Fairbanks.
Yep, we got you.
Okay, I'm gonna try to do the screen sharing and see if I can move this stuff out of the way. Are you able to see my slides?
Got it, thank you.
Okay, well, I think our last two presentations were more researcher type folks, and I'm more of a practitioner. I'm a forester, and I'm not going to give you as much data, but what I'm hoping to cover is some basics of the carbon cycle, which we got first off in the morning, and then how trees use carbon themselves, and then kind of the dynamics of carbon within a forest. And hopefully I have a bunch of pictures. This picture behind here is a picture of a defoliation event that was taken by the Forest Service in 2022 of western black-headed budworm in southeast Alaska. First thing I wanted to do, I know we covered this a little, but was just look at the concept of carbon pools and fluxes in a carbon budget. So we've got carbon stored in pools, like the soil and permafrost or in individual trees, and then it moves from one pool to the other. So for example, we can have trees doing photosynthesis, and they will take carbon out of the atmosphere and put it into the forest, or a wildfire burning. And the big ones when we're talking carbon offset projects that we're interested in is in the above ground pool in forest vegetation. And so just to illustrate this, I have a couple pictures of different carbon pools. The one on the left is in Fort Graham, and we've got some carbon in the atmosphere in the sky that we can't see. We've got carbon in the trees and carbon in that wetland in the soils. And the picture on the right is a large carbon pool. It's a big coal deposit, and there's a lot of fossilized carbon there that theoretically is going to be released when it's burned for heat or energy. The other thing I wanted to look at was just fluxes of carbon. And like I said, that's the movement of carbon from one pool to the other. And the picture on the left is from, I believe, the Funny River fire in 2014 on the Kenai Peninsula. And so that fire is releasing a lot of carbon dioxide. It's moving it from the pool in the forest to the pool in the atmosphere. And the graphic on the right is a tree growing, and that's supposed to represent trees photosynthesizing and removing carbon from the atmosphere and moving that into that terrestrial pool of carbon stored in our forest. And I saw, I think, is our first presentation had a graphic similar to this that was more updated. This one's from 2001 from the Intergovernmental Panel on Climate Change. But this was very simple, and it shows a couple different pools and their relative size. So you can see 730, I think those are petagrams of carbon in the atmosphere, 2,000 in forest vegetation and soils. And you can see the fluxes. You can see a forest naturally emitting about 119 petagrams of carbon, absorbing about 120. And then we see 6.3 at this time were emitted through fossil fuel burning. And where carbon projects come in is are you guys able to see my mouse on the screen, or would I have to use a pointer?
Got it.
Okay, so these red fluxes here that say changing land use, the concept of a carbon project is that we can change our land use and maybe increase that flux of carbon into the forest, or decrease the flux of carbon going from the forest to the atmosphere by increasing our storage. And that's where landowners can be rewarded for storing carbon or preventing the loss of carbon from their forest. And that concept there is that we'd be offsetting the release of fossil fuel burning carbon. So that's kind of a real basic crash course on a global carbon cycle. And I wanted to look at one graphic here from a carbon credit protocol. This is the Improved Forest Management Protocol through the American Carbon Registry. And this is a list of carbon pools that are included and excluded from that rule set. And what you can see is the major pools in these are the above ground live biomass carbon and the below ground live biomass carbon. The dead standing wood in the forest and the dead wood laying on the ground and the dead roots and carbon stored in the soil are optional. They're not required to be measured for these protocols. And if you look down at the bottom, soil organic carbon, like permafrost, is actually excluded. It's difficult to measure, and I'm not aware of many carbon credit protocols that have managed to deal with the carbon stored in soils. So it's largely overlooked through these carbon offset programs, although there may be some new rule sets being developed to handle that pool of carbon. The next thing I wanted to do was look at our tree level carbon. So what does an individual tree do with carbon once it photosynthesizes it and removes it from the atmosphere? And the first thing I thought I might show you is a graphic of just basic photosynthesis and that chemical equation. And so what we have is a tree is absorbing carbon dioxide through its leaves. And that's shown in the chemical equation. There's 6 molecules of carbon dioxide, and they're combined with 6 molecules of water. And we add sunlight through the leaves, which provides the energy for the chemical reaction, which creates sugar and then oxygen as the waste product. And that sugar or photosynthate is then allocated throughout that tree for various uses. And I wanted to cover the prioritization of the use of that sugar throughout the tree after the photosynthesis happens. And so the primary use of carbon after photosynthesis is in tree height growth. And I want to show this picture here, and I want to draw your attention to the ridge line. This is also a picture from Port Graham. And even though these trees are not all the same age and diameter, when you look at the ridge line, they're almost all the same height. And so what the trees are trying to do is gain a height advantage over the trees next to them so that their leaves can have more sunlight to drive that photosynthesis. The second most important use for a tree is to grow roots and leaves. And here are 2 graphics. The one on the left is a it's a rhizotron, so it's a soil pit that was dug, and then there's a window so that you can monitor root growth throughout the season. And the different colors of marker here, the red, the green, and the white, are all root growth during the growing season in the same year. So it's common to have a flush of fine roots, and then those roots will die and turn over annually, just like you would see in a hardwood or a conifer tree. And the picture on the right is the fall colors here in Alaska. And so those leaves are grown annually, and then at the end of the season, they will die and fall off. And so that tree is prioritizing a lot of energy into that growth of those roots and the leaves. So the leaves are gathering sun, and the roots are gathering nutrients and water for that tree. And we find the same phenomena in conifers. It's just not quite as dramatic as with hardwoods. A needle on a conifer tree might have a lifespan of anywhere from 2 to 10 years, depending upon the species and the environmental characteristics. And so that tree is annually replacing needles, although not 100% of the needles on the tree every year. The second use of carbon is in diameter growth. In forestry school, we also call that luxury consumption. And if you're growing trees for wood or carbon storage, that's usually what you want to manage for is diameter growth. And I've got a couple pictures here. The picture on the left is a picture of the forest in Port Graham. And if you remember the earlier picture where I showed the ridge line, these trees are all roughly the same height. But when you look there in the forest, you see a lot of different diameter sizes. And you can see that a little more clearly on this picture in a hardwood forest. This is actually in Missouri or Mississippi. It's an oak plantation. And those trees are about 19 years old, so they're all the same age. They're all approximately the same height. And there's a thinning that's going to happen here. And the trees with blue ribbon, which are a smaller diameter, are going to be removed. And the trees with orange are going to become the crop trees, or the trees that are going to grow to maturity for a forest harvest at some point. And what you can see here is that the trees that have attained, a good canopy position, have good leaves and good height, and are photosynthesizing, are putting on a lot of diameter growth compared to the trees that have been outcompeted, and they're skinny and they're weak. And a lot of times you'll see that here in the winter with snowbend, are trees that haven't been able to put on that diameter growth are more susceptible to snowbend than trees that have a stronger trunk and more diameter. One of the fourth uses of carbon is defensive chemicals. 2 of those that folks might be most familiar with are tannins and terpenes. Terpenes are used in turpentine, and tannins is the what dries your tongue when you eat grapes or drink wine. And those are not always consistent from on an annual basis. That typically when trees have damage or herbivory or are attacked, they will have a defensive chemical response. So it's kind of an on-off sort of system where a tree can produce put a lot more energy into defensive chemicals when it's under attack. And I just wanted to show you this picture. This is from the Southeast United States. And this is folks, this is probably the 1800s, and folks are harvesting pine sap to distill that into turpentine and naval stores, which were used for like wagon axle grease and waterproofing before we really had a petroleum industry. These products were derived from the forest and the defensive chemicals that those trees were capable of producing. And the final major use of carbon in a tree is in reproduction. And reproduction can be a huge use of carbon in a tree from time to time. And what I mean by this is, this picture here is a avocado tree, and you can see all the damage where the paint is on the bark. And this tree has been girdled on purpose by a farmer in this orchard. And so what happens when this particular tree is girdled is the tree, I don't know if it thinks or it senses that it's going to die, and it has a large reproduction response. And so you can have a tree have a bumper crop of avocados by girdling it and kind of tricking that tree into thinking it's dying. And so in a situation like this, those carbon reserves are allocated for reproduction, kind of a last ditch effort to save not necessarily the tree, but the next generation when that tree thinks it might be on the way out. And so these are those 5 kind of priorities for a tree. Again, height growth, roots and leaves, the diameter growth, defensive chemicals, and reproduction. So now I wanted to look at what happens at the forest level. So we kind of looked at what's going on at a tree level, and we can imagine how disturbance, fire, insects, wind might affect an individual tree, but how's that going to affect the forest as a whole? And I'm sorry this graphic is a little bit fuzzy. This is from Terry Chapin's terrestrial ecosystem ecology textbook, and I couldn't find a better graph, so I scanned this and pulled it out. But what we have on the left is our carbon flux, and this line right across the middle is a net zero. So the system is not gaining or losing carbon. And then the axis on the bottom here is our stand age. And initially, our first talk talked a little bit about net primary productivity, which is our top line. It's the gross photosynthesis of the ecosystem. And the bottom line shows respiration of heterotrophs in that ecosystem. And if we take the net productivity and we subtract the respiration, we get the net ecosystem productivity shown in the solid line in the middle. And I'm going to show a few different graphics with this and some pictures. But first, I want to look at carbon accumulation in a forest over time. And you can see we've got 2 lines. We've got soil carbon and plant carbon. And it's kind of a sigmoidal growth curve where when the forest first starts growing, it's relatively slow. It picks up and puts on a lot of carbon. And then at some point, that growth kind of flatlines. And we're not seeing accumulation of carbon in the forest anymore. And I'm going to show you some pictures with both of these 2 charts to try to illustrate this in your head. The first picture is a previously cut over Sitka spruce stand, and this is about 10 years after harvest, and you can see a lot of young trees. And so we're about where the yellow arrows are on these 2 lines. So there's not much carbon accumulated in this forest, and our growth rates are relatively low, but they are positive. We are accumulating carbon. And we move down the road maybe 10 years from there, and you can see our forest is a lot more dense, full of trees. They're still not particularly large, but our carbon flux into the system is increasing and our storage is increasing. And we see the same thing here with another stand, maybe 30 to 40 years old. We're getting close to maximum growth of the stand, but we're not quite there yet. And then here's a fully mature stand of Sitka spruce. And in this case, we have quite a bit of carbon stored in the system. We're not quite maxed out yet. The trees are still growing fairly quickly, but they're not growing as fast. They will not increase in growth rate anymore. If you look at this NEP curve, we're starting to decrease and we're approaching the neutral phase where we have zero change in our carbon stocks in that forest. And then this is a picture of a Sitka spruce forest here again, and this is what I would call an old growth forest. At this point, you can see we have young trees in the foreground, we've got old trees in the background, and underneath all the brush, there's some down logs. And in this case, we're no longer gaining carbon in this ecosystem. We're storing carbon and we're not emitting or gaining, it's a net neutral. So what we have happening is old mature trees are dying, they're being replaced by young trees. And we've got a good storage of carbon. So what I want to do is kind of tie this to a carbon credit project. This is an example project from the American Carbon Registry Improved Forest Management Protocol I had mentioned earlier and showed the table with the different carbon pools. And I'm going to flip back here, but if we think of this kind of plant carbon on this lower curve here is equivalent to the green line in this graph. So this is our total stored carbon in plants in the system. And the way these carbon projects work is we calculate a baseline stock or a baseline scenario. That would be the scenario if we were actively, doing timber harvesting, and we look at what the neighbors' forests are doing, and we will reward landowners for having above normal carbon stocks. And so that's demonstrated here in this graphic by this green shaded area. And so you can see everywhere you're going to have a dip is due to some disturbance in the ecosystem, some loss of growth, and that's going to be a negative impact on the project owner or whoever's developed that carbon project. And I want to bring this back here to our net ecosystem productivity graph. And this arrow here represents a disturbance. And when we have a disturbance, whatever type that is, whether it's a fire, a defoliation event, a landslide, a blowdown, we're going to have some loss of carbon initially, the recovery of the forest, and we start gaining carbon. And then it's going to eventually go back to our kind of steady state old growth forest where we're no longer gaining or losing carbon. But that initial loss and the disturbance can cause a problem for our carbon project. And I've kind of broken in my mind our loss of carbon into two types. We've got a fast loss of carbon from our system that happens on a short time span. So that could be due to fire. And the picture here is a picture of the Funny River fire in 2014 on the Kenai Peninsula. A blowdown event, maybe landslides or river erosion or spruce bark beetle. And the one thing I want to bring out here is this is a theoretical graph here, the same carbon project, but I drew in red here our carbon stores if we have a disturbance. So whatever that disturbance may be, we lose carbon, it will eventually recover, but we run into problems when our carbon stocks drop below the baseline. And kind of some of the impacts to a project owner would be loss of revenue or perhaps the ending of the project if the carbon stocks fall far enough. And this is a graphic I borrowed from the U.S. Forest Service. And the point here is that not all disturbances are equal. And this is a picture of a forest after fire. And you can see we've got some areas that were severely burned, where it says totally burned. And if you look at that forest, there's really nothing left except burned sticks. And then we've got some orange areas that had a less severe fire. And then we have unburned areas within a fire perimeter. So if we were to think, for an example, we had a project of 100,000 acres and we had a wildfire burn 50,000 acres, we have not necessarily lost all of our carbon on our whole 50,000 acres that burned, but maybe portions of it have lost and other portions have retained that carbon, depending upon the severity of the fire. And this kind of concept can be, regardless of your disturbance, you have those same gradations of how severe that disturbance was. The picture here on the left is of spruce bark beetle mortality. And you can see this forest appears to have lost all of its spruce component, but the hardwood component, the aspens or the birch behind it, are still green and healthy. So we've lost carbon, but not all of it. And then when you look on the picture on the right, this is a picture of a landslide in Sitka from 2015. And you can see all of the carbon was lost or at least all the above ground carbon was lost in the landslide where the landslide occurred. But the landslide didn't impact that entire area. It just impacted this one small area on the hillside. And I want to go back to this graph. So, our disturbances here, this decrease in carbon, it can be a precipitous drop, like dropping off a cliff, or it can be more gradual. But where we run into problems is where we cross the baseline. And the carbon protocols have a way to deal with this. But I want to bring up, this was a recent article that was in the Fortune magazine. I just have the headline here. And it says carbon credits are literally going up in smoke as wildfires threaten their sustainability. And so what happens when we have a disturbance on a carbon project is if the loss is severe enough and large enough, we're going to have an immediate reversal. Other impacts could be that that carbon credit offset, they're going to be eliminated. Not necessarily the project, but because of the loss of growth and the loss of trees in the forest, the project owner is going to lose revenue. They're not going to generate credits. And then they may have to dip into the buffer pool or outright cancel the project. And I haven't brought up the buffer pool, but all of our carbon credit protocols have the concept of a buffer pool where a risk assessment is done on the project and a certain percentage of credits issued are put into a shared insurance pool called the buffer pool. And if you have a natural disaster, the buffer pool will replace your credits. And this headline article here is getting at the fact that it appears that many of our carbon credit protocols, the buffer pool is not large enough to cover the speed at which the disturbances are causing reversals on our projects. So for example, in the California cap and trade projects, they have a 100-year lifespan, and we're anywhere maybe 10, 15 years into that lifespan of these projects, and we've used more than 10 to 15% of the buffer pool to cover losses due to disturbances. And this is a quotation from the American Carbon Registry Improved Forest Management Protocol I've been using as example throughout this talk. But what it states is that projects will terminate automatically if the reversal causes the live biomass carbon and dead wood to drop below the baseline. And so if I go back here, if this red line crosses our gray baseline, the project is killed, and all those credits are then drawn out of the buffer pool to cover the loss of the project. So we have other disturbances that are slower losses of carbon, and they may or may not drop below a baseline. And I have a few examples here from Alaska. This picture is the black-headed budworm, and this is in Southeast Alaska and is a defoliator that hit conifers very heavily. And I have some data from the Forest Service that in 2022, they mapped 684,000 acres of black-headed budworm damage in Southeast Alaska. We have a new guy here in Alaska, the aspen running canker. It was recently identified in interior Alaska. This one affects aspen, and it seems to cause mortality to trees fairly quickly. It's not as large scale, but it is becoming more significant, and it's new to Alaska, which is something we haven't dealt with before. The picture here on the right is the amber mark birch leaf miner. This guy is an exotic species to Alaska as well. And it doesn't kill trees, but it affects the leaves of the trees and their photosynthetic capacity, which of course is going to reduce growth. Here's a picture of spruce aphid on the left. This is an introduced pest, and it defoliates spruce trees. And then what you might be more familiar with in interior, the aspen leaf miner, which really hits aspen and reduces their photosynthetic capacity. And so these disturbances may not outright kill trees, but what they are going to do is reduce growth. And this is a graphic of tree rings, and someone has gone through here and marked it up for you. But what you can see here is that our initial growth on this young tree has got wide growth rings. It's growing fast. And they say here that we have got thick rings with high precipitation, and that could be good growing condition. And then we have thin rings with low precipitation, Well, we could substitute low precipitation with a defoliation event. And the low precipitation would be our drought. It could be damage due to fire or any one of these kind of slow disturbance events. So they're going to decrease growth, which is going to decrease the accumulation of carbon in your project. And what that might look like, if we go back to this graph, I drew in red, and I'm sorry if anybody's red or green colorblind, it's probably all going to look the same. But if our carbon stocks stop increasing and the disturbance is not severe enough to cause a outright reversal, what is going to happen is, in this case, if we flatlined here on growth, that project owner is missing out on carbon credits and potential revenue, which is due to disturbances in the forest and the tamping down of growth of our trees. And so I guess I already covered what's here in the text, but some of the impacts of disturbances on growth in our project is like loss of revenue for that project owner due to lack of growth, dips into the buffer pool from the carbon credit protocol to cover losses if that damage is severe enough or long enough in duration. And this picture here is another Alaska disturbance. This is a picture of yellow cedar decline and mortality, which seems to happen gradually over time in our yellow cedar forests. So I'm going to leave you with this picture and my name and number if anyone has questions. And this is another picture of the western black-headed budworm in southeast Alaska. And I can see that it appears to have affected both mature trees and this younger regrowth forest in the foreground. And I think we've got a break coming up, but I'll turn it back over to Tom.
Yes.
Anytime.
Yes.
And I have Shelby Sundquist. Shelby is a PhD candidate at Northern Arizona University in Flagstaff, and she used the forest model to study climate change impacts on boreal forests. And in her personal time, she enjoyed exploring the Grand Canyon. So, welcome, Shelby. Thank you.
Yeah, so thank you for the introduction. I'm Shelby. I work at NAU down here in Flagstaff. And today I will be talking briefly about future trends that we're seeing in boreal forest biomass, and specifically in the Tanana Valley. This presentation, I'm going to break it down into two parts. First, I'll talk about observed trends that we've seen, and then I will talk about some of the modeling work that we've done and things that we expect to see through the end of the century in interior Alaska. So first of all, climate change in the boreal zone, how vulnerable are these forests and the carbon in them? This is just briefly to go over the context for why we're talking about this. The climate is warming quickly. You can see that in the last couple of decades, this rate of warming appears to have accelerated. And I also want to point out here that all these years that look cold are really just cold compared to the 1960 to 2010 average, which was already warmer than it was around 1900. We also know that the high latitudes are warming faster than the global average, up to 4 times faster, reported by some papers. And this is pretty alarming because it feels like the world is already warming pretty dang quickly. So yes, obviously Alaska is included in this. It's at high latitude. Looking specifically at Alaska, I know that Uma talked about rising temperatures and rising precipitation, but I want to highlight that increased precipitation does not mean there will not be increased drought in the future. And so this and the next slide that I'll toggle between kind of show historic climatic moisture deficit and climatic moisture deficit that we could see near the end of the next century. CMD is kind of an index derived to represent the water deficit of an ecosystem, and it's based on temperature. And this is useful because we know that warm air holds more moisture than cool air. And so as the air gets warmer, it's going to increase evaporation and transpiration. And therefore there will be more drought stress if there's only the same amount of water. So to flip between these two slides, we see that historically, it's not that droughty in Alaska. And in the future, it's not going to get that much drier, at least compared to the rest of the world. But we do kind of see a consistent trend where these green areas, which are drier, get a little bit greener. All right, so kind of the first observed trend I'll talk about is drought. Drought has a direct impact on tree growth and mortality. We see that low intensity droughts result in slower growth and higher background mortality, and also increased susceptibility to pests and diseases. And one thing about droughts is that they can have lagged or cumulative effects, and these are going to become more important as droughts become more common. We also know that high intensity droughts can lead to mass mortality, and this photo here is from a big drought or a big aspen mortality event that was observed in Canada in the early 2000s following a severe drought. We also know that drought will affect competition between species because species that are better adapted to drought will fare better. And so these can lead to long-term shifts in forest composition. And finally, I want to point out that the scientific literature suggests that global forest vulnerability to drought is currently underestimated. So this could be something that's even more important than we think it is. Now, what else comes with drought? Fire. There's more of it. There is a new fire regime emerging in Alaska, which is characterized by more frequent and more severe fires burning over larger areas. And I'm sure you're all quite familiar with this by now, living in Alaska. And so I just want to point out that there have been more burned areas in the past few decades in Alaska. And also I want to mention Canada's fire season just 2 years ago, which was really historic and burned about 6 times more area than they burn on average. Another thing about fire is now that it's less cold, fires are overwintering in soils more, which means they can reemerge in the spring as soon as the snow melts, and there are longer fire seasons. So what does this mean for forests and carbon? Boreal forests appear to be shifting from a carbon sink to a carbon source. I'll walk you through this diagram, which was made by someone here at NAU. We know that black spruce stands sequester a lot of carbon below ground in these really deep soils, and that's because decomposition is slow in these soils and soil organic matter is able to accumulate. So what we see is that between fire cycles, soil carbon accumulates, and this carbon accumulates over centuries. We also know that in black spruce, fire is a normal occurrence, and seedlings can reestablish pretty quickly after a fire because these trees have serotinous cones. But when fires are more frequent and more severe, this carbon, which has been sequestered below ground and accumulated for hundreds of years, is going to be combusted and emitted into the atmosphere faster than this carbon sink will recharge. Oop. And that means that the area can become a net carbon source, which is kind of represented by this gray smoky sea getting bigger at the end of this time series. So the takeaway here is that below ground carbon in black spruce forests is released because fires are now burning more deeply into the soil organic layer, and they're burning more frequently, and so soil organic matter can't accumulate as much between burns. Fire is also driving a deciduous expansion kind of across boreal Alaska and Western Canada. The reason is that more frequent and severe fires are undermining the resilience of black spruce. So to walk you through this diagram that Victor made, fire severity kind of drives shifts between alternative stable states in black spruce forests, although through the impacts of the depth of the soil organic layer. So that's what's shown here on the left, and on the right, he's showing that fire can drive changes in forest composition when severe fire plus available seeds means that deciduous trees can colonize. So in a little more detail, black spruce stands are really resilient to fire when the soil organic layer is deep and fire severity is low. But when the soil organic layer is more deeply combusted, this is a more habitable seedbed for deciduous trees. And so these forests can become mixed between deciduous and spruce trees. And if there's another fire soon before spruce can kind of grow up in the understory and take over the stand again, then the site is likely to shift to a fully deciduous forest and remain that way because there's not really long fire intervals like there were in the past. And that's also represented in this figure on the right, where we see if there's a longer time between fires, then these mixed forests can return to spruce. But now that we're seeing more fires, it's more likely that mixed forests are going to have more deciduous dominance in the future. So what does this mean? It could mean that there's a long-term shift in the ecosystem state. And while deciduous stands may transition back to spruce during long fire-free intervals, that is no longer likely in today's climate. I want to show you this bottom figure, which comes from satellite remote sensing data over much of boreal Alaska and Western Canada. And the thing I want to emphasize here is that there has been a pretty substantial decrease in the area of evergreen forest over their study area between the mid-80s and the mid-2010s. What else does this mean? It means that more carbon is going to be sequestered above ground than below ground because deciduous forests store more carbon in their tissues than in the soils. And there are some recent findings that suggest that the increased productivity of deciduous forests like aspen and birch may be enough to make up for carbon losses from burnt black spruce stands. But this kind of relies on assumptions about the amount of below ground carbon that is combusted from the black spruce sites, and also the future health of deciduous forests. Finally, there is an idea that increased deciduous dominance may decrease landscape flammability. This is because deciduous forests are less likely to burn. They don't burn as hot. So there's kind of the idea that if we have more deciduous forests in the area, they can act as a fuel break. And even as the climate continues to get warmer or drier, because the landscape is less flammable, we won't see as many more fires as we would have expected. But there is some even more recent research going on right now, and it's not yet published. And it does suggest that when fire weather is really extreme, just about anything will burn. So that's kind of why I put this asterisk here. We don't know on this yet. Another trend that we're seeing in boreal forest today is more pest and pathogen outbreaks, both for emerging and expanding diseases, which are made worse by climate change. We know that warming temperatures can drive outbreaks of bark beetles. This is because historically these outbreaks have been cyclical when mature trees and deadwood accumulate, but now warming is improving the overwintering survival and making it so that these beetles can reproduce in 1 year instead of 2 in some cases. And also, trees are less resistant to attacks when they're stressed by drought and they can't produce as much resin. So in the future, we may see that bark beetles establish endemic or permanent populations, which can perennially damage forests and cause even larger outbreaks. This photo here is an example of the bark beetle mortality in southwestern Colorado. There's been a pretty unprecedented outbreak in the Rockies, which began in the 1990s, and it has a much larger extent, higher mortality, and has been going on for a much longer time than people have seen before. We're also seeing more diseases which are affecting aspen, and we don't know a lot about these diseases yet because we've really only seen them recently. But this photo here shows aspen running canker, which was talked about earlier, and this seems to cause really rapid mortality. And this photo on the bottom is aspen leaf miner, which seems to reduce growth in aspen. We're not really sure what the drivers of these diseases are yet, so we don't know how severe they could be, but it's a little alarming because we do expect to see more aspen and deciduous forests in the future. And these diseases increase uncertainty in the ability of the deciduous forests to store carbon. We're seeing other climate-driven disturbances occur on a smaller scale, and I'm not really going to go into detail on these, but I did want to mention them. There are more frequent storms, and we're seeing permafrost thaw and thermokarst wetland formation. So part 2 of this talk is going to be looking into modeling in the Tanana Valley State Forest that we've done, and kind of looking at what we think we're going to see through the end of the century in this forest under different climate warming scenarios. And I want to mention that for the last 3 years almost, we've been working with the Tanana Valley State Forest Citizens Advisory Committee to model outcomes of climate adaptive management that they propose. And this was intended to help inform their updated management plan. But I think it's also pretty relevant for this discussion today. And then as part of this work, we published one paper and we have a second manuscript almost ready to publish. Okay. Oh, hang on, let me change my cursor type. There we go. This is a little animation that Adriana Foster made to describe our model. We have a model called UVA FME. The name and acronym really isn't that important. And what it does is it scales up dynamics from the individual tree level to the stand level. And so what we do is we put in input for site conditions and climate, and then the model will simulate the establishment, growth, and death of individual trees on each site, and also calculate soil and field characteristics, which means that it can simulate things like fire and forest management. And then we have lots of outputs, which include tree sizes and volume, and fuels characteristics and stand type, and many more things. So this is just kind of a neat animation that shows how our model works. Alrighty, oops. Okay. I do want to give a note about climate change inputs because this is kind of relevant for explaining the results that I'll show in the rest of my talk. We use output from global circulation models to simulate future climate in UVA FME, our forest model. These are different models that other people are using to try to predict what's going to happen with future climate. And the biggest uncertainty for these climate models is how many carbon emissions humans will emit. And so they deal with this by making several different pathways for future emission scenarios, and looking at what the future climate could be depending on how much we emit today and in the next few decades. So for the rest of the slides, I'll kind of be talking about historic and SSP2 and SSP5 emission scenarios. And I will use these colors to represent them. Historic climate for me is looking at the 1960 to 1990 means in Alaska. And SSP2, SSP stands for Shared Socioeconomic Pathway. And really all you need to know about SSP2 versus SSP5 is that in SSP2, we're not emitting as much as we would in SSP5. And as a result, it's not as warm at the end of the century as it would be if we emitted a whole lot more. So this is kind of looking at what seems likely to happen in terms of future emissions. And, oops, I'm going to get my laser pointer back. SSP2 seems like a pathway that we are likely on, and SSP5 is a pathway that we could be on if the world decides to emit a whole lot more carbon over the next couple of decades, but it kind of does seem like the worst case scenario. Hopefully it's the worst it would get. So now transitioning into some of the modeling results we've had. Looking at forest change, we see that in warmer scenarios, overall forest biomass decreases. To look at this figure, I'm just looking at biomass across the entire Tanana Valley State Forest at 40-year intervals. And what I'm doing is I'm comparing what the model predicts if it ran to year 2100 with each different climate scenario, which means that the processes in my model aren't, by comparing what would have happened in each year under each climate scenario, I can kind of take out the weird idiosyncrasies of my model and kind of look at what we think is the actual difference that climate change will cause for the forest. And so what we found is that by year 2100, there could be a 28% decrease in overall biomass for the forest. And that's looking at the difference between this blue bar here and this red bar. And that's pretty substantial. How does forest composition change? We see that in warmer scenarios, black spruce stands often transition to deciduous and reproductive forests. To walk you through this figure really briefly, the x-axis is time, and the y-axis kind of shows the thickness of each of these colors is the proportion of forest cover on the landscape. So in year about 2015, there's a fair amount of black spruce and a fair amount of deciduous and mixed forests. But then when we look at year 2100 and we compare between the historic climate scenario and the very high emissions climate scenario, we see that if a lot of carbon is emitted and the climate gets very warm, we'll have a lot more deciduous forests and reproductive age stands at the end of the century than we would have had in the historic climate scenario. A few other changes that we expect to see as the climate warms in TVSF, or kind of the drivers of these changes, are that black spruce will become slightly more productive when they are growing at really cold sites, because their limitations by cold and by permafrost and by low nutrients will be slightly reduced. But drought limitation increases a lot at the warmer sites, which are mostly occupied by deciduous stands. And as a result, we see that deciduous forests are a lot less productive than they are today. And this accounts for the biomass loss that we saw by the end of the century on the previous slide, because increased black spruce growth at some of those, the coldest of the sites, does not offset that loss at the dry sites. Now transitioning from forest change to carbon valuation. Future carbon valuation obviously depends on future biomass in the forest. And this figure here kind of shows biomass across the Tanana Valley State Forest as a line under each climate scenario. And we see that in the two warmer climate scenarios, SSP2 and SSP5, biomass diverges around 2060, where losses are greater in the warmer climate scenario. And so this difference here is about an 11% decrease in overall biomass for historic to SSP2 by the end of the century. And again, that nearly 28% decrease between historic and SSP5 by the end of the century. Now, I want to make the caveat that this is total forest carbon, and it is not carbon additionality or the value of carbon offset credits in TVSF. Importantly, carbon credits are meant to pay for additionality, which is the carbon that would not have been sequestered without payment. Additionality comes from management actions that would not have been taken otherwise. And so it's kind of nice that we looked into probable future management scenarios in Tanana Valley State Forest, because we have an idea of what would happen without payments now. So to look at management in the TVSF, what actions are most likely? Well, there's some harvest and there are some fuel treatments that are likely in the future. But really the only thing that needs to be paid that much attention to in this figure is the units on the y-axis, which are less than 1 kilometer squared of area harvested or treated per year, which is a really small area for management to occur on. And it's not projected to increase very much in the coming decades. We also found that between the business as usual approach, which was looking at forest harvest data from about the 80s through the 2010s, between business as usual and between the adaptive approach, which is what was proposed to do to help deal with some of the climate change impacts that are anticipated, there wasn't really a big difference in magnitude for these two approaches. And so we saw that there wasn't a significant difference in forest composition or volume at the landscape scale. And that's just the landscape scale and not like site to site. So what we're seeing is that there's not a lot of management happening in the Tanana Valley State Forest, which means there's not a lot of potential to reduce future harvests to save carbon. But carbon offsets could pay for other management practices, which can increase carbon sequestration or reduce emissions. And And so this is not work that we've published on, but it's kind of things I've gotten to thinking about in the context of carbon credits and the TVSF and a lot of fire and biomass loss likely in the future. First, we know that wildfire is driving the future trends in forest biomass. And this figure here shows clearly that there are more fires under warmer climate scenarios. We also know that black spruce are the most abundant and flammable forests in the Tanana Valley State Forest. This figure here is showing area on the x-axis, and you see that black spruce, these blue dots, has the largest area of all the forest types. And it also has the highest intensity fires on the y-axis. But not all fires in black spruce stands are high intensity. So what makes the difference here? Actually, the statistic for this little glob of dots compared to the low intensity black spruce fires is that some of those fires will burn 12% of those fires will burn 31 times more intensely than all the other fires in black spruce stands. So to tease this out and try to figure out why this is in our model, we were looking at some of the variables that we think affect fire, and we found that the sites with the greatest litter and branches and moss on the ground had the high intensity fires. So we think that high fuel loading is driving these fires, and this shouldn't be too much of a surprise to people. So I'm going to kind of wrap up here with a question, which is asking whether we can reduce carbon emissions from fire in the long term. I actually don't know if we can do this in the long term, and I'm kind of curious to see what forest managers might come up with to deal with this. And then secondly, can the revenue from carbon offsets cover this? Because it would probably be quite expensive and intensive management. And I really want to emphasize this in the long term because I live in the Southwest and we have seen firsthand that fire suppression does not have great long-term outcomes. And it probably doesn't even reduce carbon emissions in the long term because now we're just having our fires burn even more intensely than they would have if they had not had all this fuel buildup over the past century. So kind of the takeaways that I want you to get from my presentation are that carbon in the Tanana Valley will decline as the climate warms. And these emissions are driven by drought conditions and wildfire. And we also know that greater emissions will occur after about the year 2060 if we end up in a really high emissions scenario. We also know that deciduous forests are going to expand and replace some black spruce as the climate warms. And this is important because these stands sequester carbon above ground, while black spruce has more of a below ground carbon sink. But there's also increased uncertainty in the future of this carbon sink because deciduous forests may be vulnerable to emerging pests and pathogens that we don't know about very well, and also more extreme fire weather. And finally, I want to say again that there is the potential to achieve a greater emissions reduction or carbon additionality by reducing future combustion than by reducing future harvests in Tanana Valley State Forest. So I will wrap up here. I don't know if we have time for questions now or if we want to do that in an hour or so. But you can reach out to me with questions later if you'd like to. Here's my email. And thank you for having me.
We're a couple minutes ahead of schedule. If someone had a question for Shelby. Andrew.
Hi Shelby, this is Andrew Allaby. Just a quick question on one of your graphs about the biomass in Tanana Valley State Forest in 2100. Just
Yeah.
You can clarify why the historical climate trend also had lower biomass.
Yes, that is probably, sorry, did you have more to that question?
That's it, thank you.
Okay. That is probably because we have various processes in the model, stochastic events, which are things like disturbances and establishment of individual trees, like little things that are inherent to the model. where the model has a tendency to make certain forest types or things that might have less biomass than when we initialized the model in 2014. And that's why I'm comparing historic climate in year 2100 to very warm climate in year 2100, rather than comparing historic climate in 2014 to very warm climate in 2100. Does that answer that question?
Yes, thank you.
One more quick question.
Thanks, Tom. Thanks for the presentation, Shelby. I'm Trevor Fulton. I'm with Department of Natural Resources. Towards the end of your slide deck there, you mentioned that at least in your neck of the woods, fire suppression hasn't really been shown to be that effective in reducing carbon release, at least long-term. Now you said fire suppression, unless I'm mistaken, but what about sort of fire treatments and other activities like prescribed burns that might actually take a different approach rather than full-on fire suppression? It's on the ground stuff.
That's interesting. I don't know that there's actually been a ton of research on this, but I did find one paper kind of talking about carbon emissions and fire management in the Southwest, and I can post that link in the chat or email it to you. But going back to your question, my impression is that all the thinning and prescribed burns that are happening now, they're not able to happen on a really large scale because they're pretty labor intensive. And I think they're mainly being done to try to protect infrastructure and create fuel breaks so that when we do have fires, they won't be as big a disaster as they could be. And so, for example, Flagstaff has had a crazy dry winter. I think we've had like 3 inches of snow all winter and no rain. And so we could have a really bad fire season here. And they have been doing prescribed burns all winter, and I think they're trying to get ahead of it.
Great, thank you, Shelby. Well, our final speaker for the morning is Brian Kleinhens. He's the president of Terra Verde in Juneau. He's worked for over 20 years in Alaska as a forester and natural resource manager for the Bureau of Land Management, the Forest Biometrics Research Institute, and Sealaska Corporation. He's worked on bringing carbon offset markets to Alaska through his knowledge of forest products industry and skills in forest biometrics, mapping, forest inventory, and modeling. Brian's a certified forester. He's a past chair of the Alaska State SAF. He's a member of the Association of Consulting Foresters. He holds a BS in biology and environmental studies from Ohio Northern University and an MS in environmental management of forests from the University of Eastern Finland.
Thanks, Tom. Thanks for having me today. I'm glad to see such a large cadre of people, both in the room and online. And it's my honor to go after such a great slate of speakers. We heard a lot of great science this morning, a lot of great insight from Nathan. Like Nathan, I'm more of a practitioner. And it's really, I love Shelby's animation of that little forest stand that was growing, how lightning came down and caught on fire. That kind of stuff really works for me because it takes all these complicated science concepts and it kind of boils it down to how you can actually use it or think about it in a tangible way. I've really caught on to the bandwagon recently in smoking meat. So I know it's all you see is a Traeger grill behind everybody's house these days. I gotta admit, I got into it. I'm kind of geeking out about it. But the science behind smoking meat is actually really fascinating. About introducing chemicals like salt to make changes to the proteins in the meat, keeping it at specific temperatures for specific amounts of time. And you take something that was, essentially the worst part of the animal, the beef brisket or the pork butt, and you turn it into the most delicious piece. And the way that science is evolving in our understanding of the climate is moving so fast, so complex that I'll just submit to the group that it really has to be kind of boiled down to a cookbook in order for most of us to start to apply solutions. And just like I don't have any idea about the science really that or how people kind of discovered how to smoke these meats and convert these proteins in a specific set of ways, but I can follow the recipe. I can follow the step-by-step instructions. And what I'm gonna do today is I'm gonna share a specific way, a specific recipe that carbon credits get generated on a landscape. And I'll start out by saying that the science behind this is really deep. It's got a lot of smart people pouring a lot of work into very complex methodologies that can then be actually applied by landowners and folks that are really only going to do this. Most landowners only do this once, and it's a 40-year to 100-year commitment. They're only doing it one time. It's really got to be presented in such a way that it's easy for the landowners to implement, but it also has to be very transparent to the public, to the marketplace, to the end consumers, because the more complex the system is, the more it breeds suspicion. People fear what they don't understand. And a lot of the forestry methods that I'll talk about today in developing forest carbon offsets, they're really old methods. They're things that sometimes I was taught when I was a young forester taking forest conservation is, hey, this is how we used to do things. And there's a reason for that. It's not because we always, it's not that the science hasn't evolved, it's the transparency is really important. So I'm going to talk about a specific way. I'm going to try to do it in a very transparent, easy to understand way. I'll start off by saying that these carbon markets in general, or the globe's desire to reduce CO2 in the atmosphere, this market's really big, and trees are a pretty little part of it. So I'm a forester, I'm going to lean into the forestry, but there's things going on in technologies, machines that sit on a table and just cycle air and spit out pucks of carbon. These science fiction things are happening. There's people doing things in blue carbon and changing ocean composition to suck up carbon, mine methane capture, waste management, reducing the amount of fossil fuels that we burn by doing things like encouraging companies to drive more efficient trucks around. So it's a really big market. Nature-based solutions like trees and oceans, very, very narrow piece of it, right? And we need it all, right? A lot of it is about changing behaviors. I remember when recycling first started to be a really big thing. And, my mom taught me how, you put plastics in this bin, you put the aluminum cans in this bin. And then I watched the recycling guy come up and he dumped it all into the same bin and took it off to the dump, right? Well, that was the first stage that started to think about waste stream management. We had to start converting our mindset. We had to start realizing that we had an impact. That's where carbon markets are. The global community is starting to wrap their minds around the fact that we need to do something. And it's uncomfortable and slow to change the underpinnings of the economy. Stop driving pickup trucks tomorrow, not feasible. But we have to start somehow wrapping our minds around how we can do proactive things to have an impact. Climate markets aren't perfect. No methodology is perfect. No approach to carbon development is perfect. They get good press, they get bad press, they get earned criticism, they get unearned criticism, but it's a start. And it's important to think about that because I never like to see perfect get in the way of good. And I stole that from Chris Mason. I wish he was here because that was his quote. But what I'd like to do today is run through an example of how forest carbon projects come together in Alaska. And in Alaska, we've typically done these improved forest management projects. We changed the way that we manage the timberlands in order to encourage a larger amount of CO2 to be stored per acre. So in general, this is this streamline. We assess the project, we develop a field plan, we go to the woods, we do some modeling, we prepare a lot of documents, and then it goes through a series of third-party reviews. But at a high level, that's what's happened. Let's drill into it in a little more detail. So in order to assess the project feasibility. The first thing that we often do is we take a look at what the markets are, because it's a lot like cooking. You're cooking for a specific audience, a specific palate. In much the same way, right at the outset of a carbon project development, you got to decide, am I targeting a marketplace of compliance consumers? So these are like big oil companies who have factories and refineries in California where the government's telling them they need to create climate benefit. That's a specific marketplace that, I mean, you gotta fashion a product that those consumers want to buy. There's also a big voluntary marketplace for carbon. This is often technology companies are really interested in this, transportation companies. They're not necessarily being told by a government that they need to offset carbon emissions, but because of who they are as a corporate culture or what their consumers, like you folks that fly on airlines, demand of them, they choose to participate in carbon markets and try to offset some of their emissions. It's important to note that almost without exception, all the organizations that are involved in carbon markets are actually working several different approaches. Airlines are a great example. All the airlines want to have cleaner burning fuels for their jets. They can't get there tomorrow. They've got old jets. They take a long time to amortize. The jet fuels aren't all fit to run all jets, but they're slowly working on that. As they're working on that, they also choose to participate, some of them choose to participate in voluntary carbon markets to offset their impacts in other ways, like growing more trees. So if they choose to help us grow more trees or manage timberlands better, and I hope they do because it's great business for Alaska, then there's two main approaches. One is improved forest management, which is changing the way that you manage your forest to store more carbon. This has been done quite a bit in Alaska to date. It typically involves storing, promising not to harvest a certain amount of carbon, and then changing management slightly so that you're growing more trees over time. There's an emerging marketplace for what's being shorthanded as ARR, but afforestation, reforestation, and restoration style credits. This is a really easy one to understand because it's basically planting new trees. So somebody plants a tree, they monitor it over time to make sure it's established and it grows. Afforestation, restoration are that same tree just planted on slightly different landscapes. Restoration is an exciting possibility for Alaska because it's kind of approach that you heard a few of the speakers talk about this morning. Could we use dollars from carbon markets to mitigate bug kill from insect damage? Can we help recover from fire and essentially protect more trees standing on the stump? It's great because it builds a better forest for future Alaskans, at the same time monetizing trees today. So all these things at the outset, every forest is a little different. I mean, not every place needs restoration, right? So it might not be a great fit. So you have to assess the type of project. We also have to determine at a high level, is there true climate benefit here? Is there true additionality being generated? Is something happening here that's additional, that's going to pull carbon dioxide out of the atmosphere that wouldn't happen unless we had an active hand? We have to make sure that the projects generate enough revenue to cover the costs of development projects. It's actually kind of expensive to put these together. You don't see backyard landowners with 2 or 3 acres putting together their carbon projects. And the reason's all about the dollars. It's a lot of paperwork and a lot of modeling. You need to pay professionals like myself and my team to come in and help get through it. And the bar is pretty high. This is an example of one of the spreadsheets that I pulled up that, you know, all the data goes into and it does an assessment. It's deep stuff. But this is a cookbook, right? This was built by really smart people that knew what they were doing and then trained folks like myself and my team to put in the right numbers in the right places and make sure there's a positive result and good additionality being generated. That second piece I talked about, developing field sampling plans. So, okay, let's say, we figured out this project looks promising, it's gonna pull CO2 out of the atmosphere, it's gonna create a financial return for the landowner, or at least pay for some of that restoration and fire mitigation work. That's really important. It's not always a landowner's goal to fund some other business line. Sometimes it's enough just to get some of those treatments paid for that we've been trying to figure out how to get paid for generations. There's an old concept in forestry called timber stand improvement, TSI, which used to be a dirty word because it meant you spent money to get things done in your forests. We're starting to reach a place with ecosystem services and environmental markets that more people in the overall global community are willing to help you pay to get things done that make sense. They're willing to help you pay to prevent those fires. They're willing to help you pay to get your trees reestablished. It's just a new way of thinking about things. When we go into the second phase of developing a field sampling plan, we gotta make sure mapping's solid. So we use remote sensing, we use LiDAR, we use satellite images to map out the forest lands, forest from non-forest areas, fast growing trees from slow growing trees, maybe conifers and deciduous. And then based on all the variability, we have to figure out what kind of statistical targets we're gonna hit. Much of this work is still done with forest plots on the ground. People go out and measure specific things in specific places. That all has to be done in an unbiased way. So part of the design is we figure out how many points we need and where they need to be. And then there's the logistical and QC planning behind putting the projects together, especially with Alaska, logistics are complicated. I mean, I go to work by boat as much as I go to work by truck. Use helicopters to get around, whatever it takes, float planes, you name it. So sometimes it's all of them in one day, right? So we have to think about all these things, which road systems are closed, which are open. I've got whole road systems we work on where I gotta hire a barge just to take a pickup truck out and get started, right? There's a road there, it's not that we can't drive around, it's just that there's no town. So once we get the field design, we actually send crews to the woods, crews of foresters. I still go out on a regular basis. I took my son last summer. We went out and measured some of these spots. So you go out and you figure out where the plots need to be and you measure the trees. So this is an interesting example. When you see those pictures below is just our data collection app. We're all doing this off cell phones now. So every member of the crew has a cell phone. It's all linked to the cloud. Everybody can see not only their work, but everybody else's work. And so, for example, we were able to get to this area by truck, but I had one forest technician working a plot, synced to the cloud when they were done. And then we even had the opportunity same day for a second forest technician to revisit that plot and check on them. Because quality control is super important. The transparency piece I talked about before, everybody needs to know that you're doing a good job and you did exactly what you said you did. That goes all the way down to the field measurements. Our measurements of tree height, species, DBH need to be on the money. And so we spent a lot of time and effort with systems like this to make sure even the most basic details are covered. And you can see here how we're collecting basic tree data. This is Southeast Alaska. Things like the species and the diameter and crown. All this needs to be done in the summer. This is Alaska. So we got a compressed field season. We need to get out there, quickly get it done. Projects end to end are taking up to 24 months, 18 to 24 months to put together. In Alaska, if we want to hit that target and be that quick to get from initial design all the way through having offsets to sell, we have to make the absolute most of our field season. Can't get started in September and think you're really going to make it through the field sample portion and still make your 18-month deadline. Forests in Alaska are just complicated. I mean, these trees it's a more complicated ecosystem than pine plantations in the southern US. You know, that picture on the bottom left there, I don't know if you can see that dead log laying down, kind of right behind the tree with all the painted numbers on it, but that tree's alive. That's a live red cedar. I had to walk, and it's in the plot, which would mean it's, it's close enough to the sample point to be tallied. Well, one of my guys, put that plot in, missed that tree. I walked out to the end of that dead looking log and it was green at the top. Well, we got to account for that. The fact that that tree is there and alive and not dead. And there's lots of snap decisions on the ground and that need to be made. These guys are true professionals. I mean, I know that they look a little rugged there carrying their machetes with their big beards, but they really know what they're doing. And they have to be very detailed, meticulous when they put these carbon plots on the ground. That knee-wing tree that's there in that picture on the right, all these kind of unusual growth situations that need to occur. I mean, two guys need to walk up to that tree and put DBH in the same spot. So we do a lot of notes, a lot of detailed monumentation, both in the field and in our data collection forms, to make sure that we maintain that real transparency in what we're doing. So once we get the field data, we go back to the office and we model the carbon stocks. Nathan did a great job of this earlier today. He had a different looking graph. He had the same basic concept that over time, we set some scenario and then we prove that we're beating that baseline scenario. Whatever we do, whatever we determine as this normal situation, harvest in this scenario can't exceed growth. This is the underlying tenet of sustainable forest management that flows right into carbon offset development too. Harvest cannot, it's one of the gold rules, harvest cannot exceed growth. Now, part of that growth can be turned into monetized as carbon credits, but up to all of it, but no more than that. In the same way that if we're harvesting for traditional timber products, if we want to maintain a sustainable cut, we can't cut more than growth on an annual basis. This is I did some rough conversions for the foresters and just so you could see that there's shorthand ways to go to carbon credits. We need to take all the data from the trees and we need to convert it to carbon metrics. That's step one. Step two is we need to feed it into a growth model over time. And this is the forest vegetation simulator, which is offered by the U.S. Forest Service. This has been around for 50 years. Al Stage developed this in the early 70s for this prognosis to use in northern Idaho. I met Al Stage as a young man. And I said, "Aren't you glad that your model's being used all over the country?" And he said, "It should only be used in northern Idaho. That's where I built it for." Well, now it's being used all over the world. And the reason is it is a very well-maintained product, has a dedicated team to keep it updated. It's easy to use and it's publicly available. I talked to a lot of international folks working in nature-based carbon solutions. They're really envious that the United States has a tool like this. They're always talking about, well, you guys get to use FBS and you guys get to use that. I think it's important to point out the power of investing and maintaining these tools, that new tools like the ones that we saw that Shelby had. They really do lead eventually to market opportunities. So we put all the data to FBS, you grow on an annual basis, you make some projections forward. It puts out output. It actually now, because it's being maintained, it puts out output in carbon numbers. So we can see what the carbon stocks look like for each pool over time. You see above ground and below ground, different pools that you heard folks earlier talking about. And then once we get all the modeling done, all this complicated modeling, we have to produce a suite of documentation. This is publicly exposed documentation, has to be in a common format. So I put this table of contents over on the right. That's similar to other projects so that folks like the interested public and the marketplace can read these reports and sort of start to understand the similarities and the differences between them. But these are very detailed documents. It takes a lot of time to put these together, and they're checked very carefully. This is a key component in the transparency piece, is a third-party review. After all of this comes together, all the measurements, all the modeling, all the documents, the reports, the explanations, then it needs to be checked. And it's typically checked by 2 to 3 different layers of oversight, depending on the marketplace, depending on the methodology. But the third party piece is very common to all highly credible carbon credits in the global market. It doesn't matter what, if I'm talking about the machine kicking out those pucks of carbon, or we're talking about trees. The accountability is super important. The people that do the oversight, invaluable. So they do a detailed check of the plot, those tree measurements for our nature-based projects. They crawl around out, look at those trees that I was showing you earlier, make sure that their measurements, check our measurements. They go through all the calculations and all the spreadsheets. They rerun the FBS models to check us. They look at all of that. And then typically they make a recommendation to a registry that who acts normally as the folks that author the methodologies and the folks that make sure that consistency is maintained. So that second set of oversight from the folks that actually hold the accounting of your carbon credits is really important. It's the last step that needs to go through. Operates as a whole nother check on things. So I think it's really important to understand what a commitment a nature-based carbon offset project is for a landowner. It's a major generational commitment. A quick IFM project timeline is 4 years. That's something that not only you're dealing with, but as a forest manager, but 2 or 3 generations of forest managers after you are going to deal with. It's a contract with the buyers, but also with the global community that you're going to manage your forest in a specific way for a long period of time. I think that especially when I hear criticism about forest carbon projects in Alaska, people forget what a substantial commitment this is to undertake. All that, the annual reporting, the long-term vision and stability, that all has to be maintained for the term of the contract. Like I put out here, these at a regular basis during the term of the contract or the project, we're getting regular desk audits, we're getting regular field audits, we're updating our measurements to make sure that we're monitoring for growth and disturbance. And we got to get out there on the ground, see if the bugs did chew it up. We got to see if the fire did burn through. We got to make sure that the trees are growing as fast as we predicted with the forest vegetation simulator. Sometimes they are, sometimes they aren't. There's a lot of ongoing effort and even jobs in rural communities in Alaska that go into maintaining these carbon projects. I'm actually going to park it here. I threw this up. These are questions I get all the time. I do a lot of these talks all over the Pacific Northwest. These are all the great questions I typically get. I know we had a question and answer session later, and I know I'm at the end of my time. So I'm going to stop here and thank you again for letting me come present. It's always a joy to come to Fairbanks.
Thank you, Brian. So what we're trying to do now, I'm gonna try to reverse the video here to show the audience. Okay, and yeah, so we have Uma and Brian here. We've got Shelby and Nathan online. So at this point, we'll open up to questions. I just checked the chat. I didn't see any there. Chris Mage had to step out, but he had one question he left me with. This is for Uma. You had talked about the early snow off. And you said at this point, it's not understood, well, what the mechanism is. Are there hypotheses about what might be going on between the relationship of snow off and fire?
Oh, sorry, we don't have a hypothesis yet. We don't know exactly what's happening, so that we haven't shown what's happened. We think, okay, right, my student's calculating this stuff. So right now, this week, I would say, I think it has to do with the imposed large-scale circulations that lead to earlier snow off are also associated with more precipitation. So, and what's happening is when you have a certain phase of something called the PNA, an atmospheric teleconnection, you get early snow off, and then you get warmer temperatures later in the summer. So something must be happening in between there. So I think it actually is a land that it's a moisture interaction with the atmosphere that leads to a persistence of the warming. Sorry, I don't know if I explained that clearly enough.
Okay. Any other questions here? Are we seeing any online?
Got an online question.
Any?
Yeah, Adam Castor online is just asking a clarifying question. Did the FPS model the growth in yield and then FVS for the carbon outputs? Or did you use FVS for your whole exercise? Looks like that's directed to Brian. Finance. I can repeat that.
I think I got it. Can the folks online hear if we speak from the audience here?
They should be able to, the microphones.
Oh, okay, great.
Got you loud and clear, Brian.
Yeah, so actually both models can be used or either one. They're both great growth and yield models. Commonly, we use FVS because it is publicly available and the verifiers understand it, but we've used FPS, which is just another growth and yield model as well. It's well supported and well documented too.
I guess, real quick, sorry, this is Adam Castor. Let me clarify my question better. Have you calibrated the FPS carbon outputs for Southeast Alaska and seen good data from that? I guess I didn't ask that the first go around, but that's my real question. Have you utilized forest projection and planning systems for carbon outputs for professional work and saw good stuff from it? Thanks.
Yeah, the short answer is yes. It doesn't translate directly into carbon into the market. And sometimes you need to tweak the carbon output numbers themselves. But the basic diameters and heights can be fed into those growth equations and volumetric equations, and they have really good results. So FPS does a great job of growing trees over time. Sometimes the carbon numbers it calculates are great, sometimes they're not. We typically go back to the dimensions of the tree itself, and it has great results then.
Thanks, Brian. Appreciate it.
We had a question in the room, Mike?
Yeah, this is for Brian. Typically, what's the scale or size of an Alaska carbon project that you work? How many square miles?
Yeah, no, that's a great question. So, the minimum size of a voluntary project tends to be at least 5,000 to 8,000 acres. And then a compliance project tends to be bigger than that yet. So, an extremely large project in Alaska would be, a couple million acres, but you have to have at least, somewhere in the neighborhood of 5,000 acres before you start to cover the fixed costs of having all those bearded machete wielding guys crawling around in your landscape.
There's a question in the chat from Jesse Gerke. Brian, can you briefly discuss market leakage and how that percentage is determined and whether it varies?
It does vary. It's part of the, and I'm sorry, I'm gonna give an overly simplistic answer here, but it's part of that really smart cookbook. So that I gave an example of a spreadsheet. You know, each of the sophisticated sort of class 1 registries sort of provide those kinds of tools where you put your basic inputs in, like your fire risk, like your sawmill capacity, and those things get calculated for you. Market leakage, which is, you know, what's the opportunity for some of the carbon to go off in other places, like if you're doing a harvest program, you have some slash of the landscape, right? So that you could consider that slash to be a carbon emission, because we're not going to turn it into a 2x4 that's going to go into a house. It's going to leak essentially back into the atmosphere eventually. But those are all variables that are baked into some of these methodologies and approaches.
Because Nathan had mentioned in his talk about dead wood standing around the ground is typically not part of the protocol. Is that correct?
It can or can't be.
It's optional.
Yeah, and all these rule sets, all these complicated cookbooks, they have different rates, right? If a tree is standing and dead, somebody's gone through the science to understand how quickly that tree rots standing and emits the carbon from the live tree into the atmosphere. But fortunately, folks like myself don't have to do that work. It's kind of been researched and vetted already.
The clarification, what's market leakage in this sense?
That's if the wood product would have gone into a house and been stored for a long period of time, or if that tree had been alive and it kept adding on, the carbon would have been sequestered. If carbon's draining out of the system somehow, the dead tree is slowly decaying. That's leaking. That's leakage.
Do you have an estimate of how many acres in Alaska are part of such projects? And where are they located?
So the question here is how much of Alaska is in Marcus now?
Yeah, and where are they limited to southeast?
No, there's projects everywhere from Fairbanks clear down to Ketchikan. So we have projects all over the state in all the major forest types. I think you'll hear this afternoon from Trevor Fulton about the state of Alaska's interest in participating in markets. But up till now, it's been Alaska Native Corporation landowners, and we have hundreds of thousands of acres enrolled in carbon projects statewide. I mean, it was a great question. I should know it, but I'm going to say, and maybe Nathan even knows, I'm going to say we're pushing 1 million.
Yeah, I'd throw out there, I know we've got 17 compliance projects and a handful of voluntary projects. So we're probably pushing over 20 projects, and they're minimum 5,000 to 10,000 acres. And you've got one like Otna that's 500,000 acres. So you can add those up and you're probably, 1 million acres of forest or close to it.
So most of them right now you're saying are the compliance market, is that correct?
There's a mix. You know, we saw a lot of activity in the compliance market starting about 6-7 years ago. And there, as compliance market prices have stabilized, voluntary market prices have risen to meet them. And if you have even market values, then the landowners start to think about things like length of commitment, complexity of the program. And so they say, well, I've got these protocols from folks like the American Carbon Registry and Vera that last only 40 years. And that reporting and the modeling is simpler. Maybe I'll go with that because it's, you know, it's essentially similar, even money.
Here's a question from Doug Hansen to Brian, popular this morning, Brian. Can you discuss impacts of the current logging industry in the Tanana Valley State Forest, where the predominant harvest is white spruce and birch?
Sure. Well, I'm glad to have Doug with us today. We've used Doug's reports and work to understand a lot of the forest inventories statewide, so great to have knowledge in the room. Yeah, so I mean, there isn't anything going on in the Tanana Valley State Forest yet. So there's nothing to assess impact against. Dolan Corporation does have a carbon project adjacent to the Tanana Valley State Forest. So, but I think what the spirit of the question is what's the impact likely to be on timber harvest operations? And I guess I'll say that there is dynamic tension between carbon markets and traditional timber markets. Carbon markets don't exist without traditional timber markets because you have to prove that additionality. And then without carbon markets, we're not achieving the full potential value of the resources of Alaska's timberlands. So they're two ends of the same system. It's all part of the timber industry. It's not a ton different than evaluating the difference between log export markets and domestic manufacturing. We've been doing this kind of thing a long time as foresters, just with different labels. So the question will be, as if and when carbon projects come together on the Tanana Valley State Forest, how do the details of that project look? How are the species treated? What's that baseline scenario going to look like? Where the harvest is going to happen and how?
Yeah, Brian, this is Doug. What I was trying to get at there is that, our annual allowable cut obviously is much higher than what we're harvesting. But especially in terms of white spruce, we're harvesting, when you divide the allowable cut up into different species types, we're not that far below in white spruce sawlog. And so I was just curious of how that affects that, when you look at just portions of the forest.
Yeah, I mean, we've got sort of an embarrassment of riches in Alaska. I mean, we've got so much forest land and so much growth. Between the traditional timber products market and the carbon market, we could utilize all that growth right up till the total growth. And we're not even close anywhere, not on state lands, not on private lands, not on federal lands, anywhere in Alaska are we even approaching our annual allowable cut. So it would be it's an interesting question, especially when you start to subset the forest and we say, well, what about a specific species? What's the annual allowable cut on that? And if species have a higher value in the timber market than they do in the carbon market, right, that dynamic tension is going to play out. So the trees have to, it has to be economic to move the timber in a conventional sense for the carbon markets even to be interested. So, understanding that harvest of spruce, white spruce volume and the growth rates of spruce white spruce volume is really important because that's kind of the most lucrative piece of the interior's timber base, right? A lot of times that carries the rest of the operation is the white spruce sawlog harvest.
Okay, I apologize to Keith Coulter. I missed Keith and there, you might have had your hand raised. Go ahead, Keith.
Hi, can everybody hear me okay?
Yes.
Yeah, thanks for taking the question. This is probably a larger room question. I appreciate the academics and their presentations in terms of their literature supported evidence-based type materials that they provided. I guess one of the biggest, I've been to several of these now, and we never seem to be asking the question, are the carbon offsets working? Because in the information that I can find that's academically peer reviewed is that there's no evidence to support carbon offsets are working at all. Carbon appears to be increasing in the atmosphere, and that these projects actually are exacerbating the problem of carbon in the atmosphere because they're allowing the biggest polluters to pollute. And I'd like to, I keep coming to these things. I never see any evidence-based documentation that says these are the carbon offset projects. This is what they're doing in terms of actually reducing carbon levels in the atmosphere. And I'm interested in to hear what the academics think about this, because surely they must read the same materials that I'm reading. And I guess it's like an interface between a cleverly poised marketing scheme, and then they keep throwing science in on top of it. And I never see the science from the actual carbon developers themselves. It's basically no checks and balances. They talk about third-party auditors, but they work for the carbon developers themselves. So I guess I'm not a convert. I don't think that everything's going to be great in the end. And I'd like to hear, maybe I'm wrong. Maybe there's a literature search out there that provides all this information and I just can't find it. But I'd love to hear from the academics who have real numbers and actually do literature searches and those types of things, and have a solid answer on how they are actually benefiting by removing carbon.
Keith, that's a really good point. This is not my area of expertise, but I think I've read a lot of the same literature you're alluding to, which talks about how claims of the amount of carbon on a site could be exaggerated, or the amount of carbon additionality are exaggerated grossly, or leakage, which is when there could be a carbon offset project on one site, which stops that site from being clear cut, but then an adjacent area is clear cut instead because there's still the market demand for the timber or whatever product. And there's a lot of literature that says 90 to 95% of carbon credits that are sold don't actually prevent carbon emissions or result in more carbon than would have been in the ground otherwise. And so this is like a really big picture question about the viability of the carbon market and whether it's actually the solution that we're looking for to the climate crisis. And I kind of feel like it's not going to be the solution, but it's this big market. And yeah, I kind of feel like there's a lot of momentum behind the market, and especially momentum from people who are making money off the carbon market. And I don't know what to do at a policy level besides try to make sure that if carbon credits are sold, they're actually making a difference. Because
I guess, not to interrupt you, but every one of these talks, I always hear about how complicated the carbon market is from the developers. And, if they talk about it being transparent, but they never provide, their methodologies. I guess I'm baffled. If it's this effective, why aren't we seeing it from the academic side? You guys know how to measure things at the college campuses, and why aren't we seeing the results in terms of your little graphs going down instead of always up?
Yeah, I think because the people who are making money off it in various industries are, it's like, let's prop up this whole market, but I don't know that the market is doing a lot in terms of actually reducing emissions and reducing future warming. But like, academics aren't policymakers and we're not marketers, and
it's a slippery slope, though. It's the thin end of a wedge. I mean, they're at least in Alaska, where we're basically reliant on public land for timber, and we're going acre to acre. If carbon gets an acre that's taken away from industry. So it has real ramifications. And these developers can't really seem to demonstrate their effectiveness. And why? And again, the SAF is leading some of these talks. They use the word scientific quite a bit. I guess if it's scientific, why can't it stand on its own 2 feet? Because the ramifications for those of us who make our livings out of products, it has real effects. Thank you.
I've got 2 comments, if it's all right. I've thought about this, and there's a couple criticisms you could make of the way the carbon credit protocols are designed, right? You're essentially not harvesting wood. And so you're not removing more carbon from the atmosphere, so you're not going to see that in the short term. If you play that out for 100 years and you take 100,000 acres of harvesting off the board, well, you might see some difference there because that carbon pool isn't depleted. And whether or not, I think one of my biggest criticisms of the cap and trade protocol out of California is that when you develop a project, you have to show that it's economically feasible to harvest your timber. And all you have to show is that you'd make $1. And so if you'd make $1 harvesting 10,000 acres, is any landowner actually going to harvest that timber? But it meets it meets the rules of the protocol. So, but maybe almost certainly over 100-year lifespan of that project, the timber markets go up and down, and maybe that would be harvested probably when we have another, spotted owl listed as an endangered species and the timber market spike. I don't know. These are just things I've thought about, not necessarily an answer. And another area that's been pretty well documented in some like investigative journalism, and I'm not sure about the peer-reviewed literature, but the size of the buffer pool, these percentage of carbon credits that go into a shared risk pool to cover losses due to natural disasters. There's some evidence that seems to show that those pools may not be large enough. So the contribution of those buffer pools will be depleted before the lifespans of the projects are up. And so those are two areas where, the rule sets are already set, the projects are in order, and hindsight's 2020. But the buffer pool issue with increased wildfire season and then increased insects and bugs killing our trees might make those so they don't quite work out the way that initially planned.
I have one other comment in terms of the SAF. It seems like it's very difficult to do any review on carbon projects without them explicitly talking about, reducing logging. There doesn't seem to be any distinction made between forest management and the tried and true methodologies that, are there to increase vigor, reduce species competition, and all those types of things that make fire danger go down or trees grow longer. There doesn't seem to be any distinction made when we talk about carbon, about forest management and timber harvesting as it has been applied for 150 years and how it's beneficial. You get to carbon, and it seems like the PhDs just say, not you PhDs, other PhDs, that we need to reduce or eliminate logging. And I guess 58 million acres in the Western United States that have, and Ms. Sundquist pointed this out, that have been under fire exclusion. That's what doing nothing gets you. And it seems to me that these carbon protocols are one of the poster children for doing nothing as a management alternative. And those are the effects. So I wish that we'd spend more time talking about how these things might not work, as opposed to talking about, how it's a win-win. So those are my comments. Thank you for having me.
I appreciate it.
I think those are really good comments.
Yeah, thank you. This afternoon session is really designed to get more to the bigger picture on all. So Keith, your question is very well taken. Part of the reason when Chris and I and Scott Rupp looked to invite some of the speakers that talked about climate trends, that talked about some of the modeling, is to understand and make it real clear to everybody here in the Boreal region, fire has been increasing, it's likely, and that's going to be a factor of the risk pools, and that's what we want people to discuss. One of the speakers this afternoon is going to be Spencer Plum, and he raised his hand. He works with this stuff. So Spencer, if you'd like to respond a little bit to the.
Sure, yeah. Definitely have heard those criticisms, and I think they warrant serious consideration. And I think of voluntary carbon markets as one, you're not required to do it. These companies are opting to do this, so there's no actual cap on these things. So if there was driving policy that said, okay, we need to reduce our emissions, you might be able to see that. And I think you actually do see that in California, where basically a carbon credit is outsourcing some of that. You get a certain amount of emissions, and if you can't meet that, you're either penalized or you can buy carbon credits for a certain percentage, not all of the emissions that you can't meet. So we need to think of it as a tool, but then globally, most countries, most businesses are not subject to that. They don't have to participate. And what we see just in terms of scale, Keith, I think is important. Like the carbon market reduces or removes about 150 million to 200 million tons of carbon a year. And if we think about that in relationship to, I think it was Eugenie's first presentation, it's, you know, what do we think the delta is? 1.6 gigatons a year, possibly more. So it's a literal drop in the bucket of, you know, what we can right now do in these voluntary markets versus what, you know, the potential for these markets is in the future when we, you know, we recognize that we have to reduce emissions by a gigaton or more annually. We need all the solutions we can get. So this, I think that the hypothesis for this market is, can we drive dollars to it so that it can be effective? I think it's unrealistic to expect it to be effective immediately or within, you know, 20 years of its formation when we're seeing, you know, 300 years of the use of fossil fuels and increasing use of those resources. You know, not a bad thing for society until we recognize that that has impacts on climate change. So we're trying to, you know, to get this market scaled up to balance that out. And it's hard to do without a policy driver. So in absence of that, what can the market achieve?
Glenn, Judy, at your end?
Yeah, I guess the perspective I have on this is that what makes the value in these carbon markets is two perspectives on the knowability of the future. Okay, so you have a baseline scenario. I mean, do you think this will happen in the absence of this project? And then you have the perspective of imposing this project will, we think, produce this out. So if there's uncertainty, too bad. I mean, the whole thing is completely uncertain. And we try to reduce that uncertainty and provide the best information we can to reduce that uncertainty. But just like betting markets, I mean, you got unknowables and you deal with them and you make decisions. Okay. Second thing, I do think it's a good idea to see if we can, as managers, as scientists, rummage around the storage closet here and see if we can pull out something that's other than preempting timber harvest. And here's one that's come up, and I think it's got some real potential. We know we have this Yedema permafrost, extremely rich, especially rich in carbon. It is frozen out, it's relatively shallow. And a lot of it occurs, for example, in the Yukon Flats, which is a warm summer, high fire frequency environment. Now, you wouldn't have to go to a complete 100% fire suppression policy to target the especially carbon-rich Yedema permafrost in a very large land management unit like the Yukon Flats, and make a pretty strong case that, well, okay, what's the national percentage of fire suppression budget that is expended in Alaska? And say, you know, we really got a claim on a carbon benefit basis on a much enhanced fire suppression capability specifically targeted at suppressing or reducing the gradual combustion of the Yedema permafrost.
We're actually gonna have a talk this afternoon on that very topic, so that's perfect, thank you.
Great.
So Joshua Holt has a hand raised.
But my point is there are other things that if we put our heads together, we could probably do that. And I do take the point that timber harvest is not the only preemption.
Thank you. Joshua, go ahead.
Hi, yeah, I just wanted to address Keith's point. He mentioned the do nothing, and well, doing nothing, not harvesting, in the past has kind of meant we just walked away and we didn't come back to it for 50 or 80 years, and whatever happened. The big difference I see in this is that this is creating a financial incentive to be very mindful about what's happening on this land. It's being routinely monitored, inventoried. It's not just forgotten about. And I think that's a big difference. And it has a lot of value.
I meant doing nothing in terms of cutting trees. I've yet to be told how you manage a forest without cutting trees. I mean, you can measure it, you can look at it. I suppose you can make a case that that's doing something, but in my opinion, doing nothing is when you stop cutting trees.
Yeah, and Keith, I'd just make a counterpoint. It may not be the same for old project owners, but a couple of the project owners I work with, they're initiating pre-commercial thinning timber stand improvement programs with revenue from their carbon credits that they wouldn't normally be doing because they couldn't finance that operation. And it's the carbon credit revenue that is going to allow them to do some more active management on their forest, cutting trees, just not for commercial sale.
We have one final question in the audience here.
Yeah, I had great talks this morning, and so I'm not a forester. I'm here to learn though. This has been great. So one thing that I was curious about. So, and we talk about economics. Like what? So right now, to measure our forests, it requires a lot of data acquisition. Be it your guys in the woods, or LiDAR, or some kind of remote sensing situation. Like, for Alaska to really get into the market, like, I guess, does that exist in the handbook about like what are like some of the key sources for your data acquisition, and like how do we get over that hump of getting to where like the rest of the United States is?
Brian, you work in that world. Do you have a thought on that to wrap up for the morning session?
Sure. Or you're pretty involved, so it's okay. Look, when it comes to any kind of monetizing of our natural resources, the information is the first thing. I don't care if it's oil in the ground or carbon on the stump or timber on the stump. And so I'm very supportive of ongoing programs to monitor and quantify our forest resources, like the Forest Inventory Analysis Program conducted by the U.S. Forest Service, great program. The additional acquisition of data like LiDAR. We're just a vast landscape that gets overlooked due to big numbers attached to it. So the University of Alaska Fairbanks right here is doing great work with drones to try to bring down costs of remote data acquisition. It's never going to get cheaper to send boots onto the ground in Alaska. It's going to get more expensive all the time. It's my business to send people to remote places, and I hate that it's getting more expensive all the time, but that's the fact. So we're going to have to start to lean on technology more. And some of these markets, whether it's invigorating the timber market or invigorating the carbon market, that's some dollars that are gonna, ultimately get invested back into learning more about Alaska's resource base. And we all want it to be managed sustainably. I certainly do. Our Constitution says we're supposed to do that. So in order to know that we're doing it, we better have a high degree of confidence in the information. So hopefully technology will, help provide a piece of that puzzle.
All right, let's everyone give a round of applause to our speakers in the panel. We're going to break now. We're going to keep the Zoom meeting running, but we're going to pause the recording. We'll meet back here at 1 o'clock. For those of you who've never been on campus, if you can walk just 5 minutes to the east here along the road in the Murray building, there's a little cafe in there if you want to eat there. You can eat your second lunch downstairs or whatever. So thank you.